Hello friends, in the last video we have seen how to analyze motion in 1D, that is motion along a straight line, and this straight line can be x-axis, that is a horizontal axis, or it can be vertical axis, that is the y-axis. So in that video we have learned how to analyze, how to determine its position at given point of time t1 and how to determine its velocity at any point time t1. For example, let's say if I have an object and this object is moving along this axis. So this is my x-axis. So this object is moving along the x-axis. So when I am analyzing this object, so this is a straight line motion. So object is going in this straight line. So this is a straight line motion. So this is an example of one-dimensional motion. So what is my objective? My objective is to find at any point of time, let's say t is equals to t1, what is its position? That is what is its x coordinate. So I am interested in x coordinate of this object. That is what is the position of this object. And I am also interested what is the velocity. That with what velocity this object is moving at any point of time. So these two are point of interest. First is position and the second is velocity of this object, and that was the one-dimensional motion. Now extension of 1D motion is 2D motion, that is two-dimensional motion, and two-dimensional motion happens in plane. So if you see in one-dimensional motion happens on a straight line. In two-dimensional motion, basically motion takes place in a plane. So what do you mean when I say plane? Basically when we say plane, it consists of two axes. Here in this case I have a x-axis and in this case I have a y-axis. So now using these two axes, now we have a plane. So this is my plane. So now motion will happen in this plane. Then we will call this is a two-dimensional motion. Now in 2D, motion can have a different type of path. It can either go in a straight line, something like this. So this is a straight line motion in 2 dimensions. It can go something like this, parabola. We will call this as a projectile motion. It can also move in a circular path, or it can go in a zigzag fashion, something like this. So all this is an example of two-dimensional motion. So you see, only important point when we are saying two-dimensional motion, this motion is happening in a plane. They will have different kind of path. So it is not either along the x-axis nor along the y-axis. It has a path that moves along the plane, that moves in the plane. So let us discuss some example of two-dimensional motion. The first example of two-dimensional motion is a projectile motion. You might have seen these games called cricket. In these games what we have a batsman and we have a bowler. So this bowler, what he does, he throws a ball and this batsman hits this ball. Now the path of this ball is basically example of projectile motion. So this bowler throws this ball and this goes in a plane. So this is not moving in a straight line. It's moving in a plane. So you see, this is a vertical plane. So this ball is moving in a vertical plane. Similarly, when this batsman hits this ball, this goes something like this, then this is again a plane. So this is a two-dimensional motion. So in such kind of motion, we are interested in at what velocity bowler should throw the ball so that it reaches very close to the batsman. And other word, he is also interested with what angle he should throw, with what velocity he should throw, where should the batsman at what velocity he should basically hit the ball, and in what direction he should hit the ball. So we are interested in magnitude as well as direction, and this all happening in a two-dimensional motion. So projectile motion is an example of two-dimensional motion. Similarly, when you play the football game, this is also an example of two-dimensional motion. So at t equals to 0, this ball is here and you hit this ball in this direction and this goes something like this. So in this case you are interested in at any point of time what is the x coordinate of ball. So this is the x coordinate of ball. So this is where your ball is from the origin, from the point where hit the ball. So this is your origin, that is 0 0 coordinate, x coordinate is 0 and y coordinate is 0. So in such kind of problem we are interested in where the ball is exactly at given point of time. This means what is its x coordinate and what is its y coordinate, what is the height from the ground and what is the distance from the origin. So this is the coordinate, in this case x coordinate and y coordinate. And we will also be interested what angle he should basically hit the ball, with what velocity he should hit the ball, and if he has a something in mind, some target is in the mind, goal post is in the mind, then he should know. From experience all this comes. Basically he doesn't have to do all this calculation, this comes from the experience. He has the experience, he knows with what velocity he should hit the ball and with what angle he should hit the ball, and so all this comes with the experience. And this is an example of projectile motion. Another example of projectile motion, another example of 2D motion is circular motion. So this is circular motion. So you might have some time on the roller coaster. So this is in this kind of game, or you can say entertainment. What you do is you have some buggies and you basically go onto that buggy, and that buggy goes from crest and bottom, and then it all moves along a circle. So you see what happens, this object is moving along this circle and then finally it goes to the next track. Same thing, it comes and moves. So this object is moving in a circle. So this is an example of circular motion. So what is happening in this case? This case, you see all this is moving in a two-dimensional vertical plane. So this motion basically contained in a plane, and the path or trajectory is a circular motion. So this is an example of 2D motion, because you have a plane in which this is moving. This is not moving in the straight line. It's not like this, or it's not like this, or it's not like this. So it is not moving in a straight line, it's basically moving in a plane, and in this case trajectory is a circular motion in this case. You can have a three-dimensional motion also, just to illustrate not only 1D, 2D, it is also possible to have a motion in 3 dimensions. For example, if you have something a spiral, later we will learn in magnetic field, the particle moves something like this. So they are something, this is kind of motion is called a spiral motion, something like this. So this is moving and going. So if you consider, this is a superposition of circular motion, but only thing is in this case, every time circle is not in the same plane, it's moving. So in this case the motion has 3 components. It has x component of velocity, it has y component of velocity, and it also has a z component of velocity. So when I say motion in 1 dimension, it has only 1 component of velocity, either vx, vy or vz. When I say motion in 2 dimension, it basically has 2 component of velocity, vx or vy, vx and vy, or vy and vz, or you can have vx and vz. So 3 possibility. You can have vx, vy, you can have vy, vz, you can have vx and vz. So these are the 3 possibility when you have a motion in 2 dimension. Now when you have a motion in 3 dimension, you will have x component of velocity, you will have y component of velocity, and you will also have a z component of velocity. One example is a spiral motion. You might have seen this mouth ka kuwa, or the dip, this is a death well sometimes called. So people basically try to drive a car on a spiral motion. This is example of 3D plane. So 3D motion. So you see this is going in a circle, and then it comes, next time it goes up, next time goes up. So this is the motion that takes place. So you see in this case these cars basically moves in a spiral motion, and that is the example of 3D motion, because it is going in the vertical direction, in this direction as well as in this direction also. So such are examples of 3D motion. In the 3D motion, you have to find position of object in terms of x coordinate, in terms of y coordinate, and in terms of z coordinate. So when you have this, you have to give x by z coordinate, you have to give vx, vy, vz. So now you understand, when I have one dimension motion, this is easy. So you have to give only one Cartesian coordinate position, either x, y, or z. And then you have to give only one velocity. It can be vx, vy, or vz. Now in this chapter we will also learn about the relative velocity. So in the next few videos we will see what all this means. What is circular motion, what is projectile motion, what is relative velocity. So just to illustrate relative velocity, when you sometime might be having in a train, and some other train is moving just side by yourself. So you find that train is either moving fast or it can be moving slow. So basically what you are doing in that case, you are observing another train with respect to your velocity, with respect to your position. So you are not standing. Your train is also moving. And the next train is also moving. So both train is moving, both positions are changing. So now in those cases, we cannot talk simply about in terms of absolute position, absolute velocity, because your velocity is not constant and you are measuring the velocity of other train. So you can max say something about relative. What is the relative position of that train or that guy that is sitting in the train with respect to your velocity or your position? Because you are not constant, you are moving. Then this is an example of relative velocity or relative position. So when we say relative position, that means what is the position of other guy with respect to your position. So in the next few videos, we will also see how to calculate relative velocity, what is the use of relative velocity, and how we do problems related to relative velocity. So in the previous chapter, we have learnt about different terminologies. That is, first is displacement, velocity, and acceleration. So if you remember previous videos, we have said if you have a motion in one dimension, you have to know what is the displacement, what is the position vector. Displacement means position vector. Where it is from the origin. So displacement, velocity, and acceleration. So now in this video or in the next few videos, motion related to two dimensions, we are going to illustrate those terminologies again. Only thing is, this time we will have position vector in two dimensions. Position vector, if I have a two dimension, then velocity will be having two components. Similarly, acceleration will have two components. So we can say now these quantities, that is displacement, velocity, and acceleration, will not lie in a single line. They will be in a plane. They will have two components. They will be having two components. So we summarize, if we have a motion that is in a plane, we call this a two-dimensional motion. And there are different kinds of motion that is possible in two dimensions. You can have a projectile motion, you can have a circular motion, you can have a three-dimensional motion. An example is a spiral motion. Now we will study some terminology. First is position vector. Now what is position vector? One thing is, it is a vector. That's why this is called position vector. And position, the term position means where the object is located. What is the position of that object? So when I say position vector, this means I want to know where the object is located, what vector I can describe the object. So to describe the motion of a particle in a space or in a straight line or in a plane, that is two dimension, we must first be able to describe the particle's position. So we should know where the position of the object is, and that is called position vector. For example, if I have an object that is moving in one dimension, so this is my x-axis. So object is moving in the x direction. So this is my object and this is moving. At some point of time this object is here. So this is t is equals to 0 and this is t is equals to t1. And this is x equals to 0 and this is equals to x1. So this is position vector. So I can say position of this object at t equals to t1 is equals to x is equals to x1. So in this case this is the vector. So this is a one-dimensional vector. So position is here and this is origin from where it started. So if I connect the final position, that is t equals to t1, with the origin where it started, that is t equals to 0, we get a vector. So this is my position vector and in this case this is simply x vector. So generally we denote position vector with symbol r. And arrow sign onto the top of the letter denotes this is a vector. So position vector in this case has only one component, x component. You can also have a motion that takes place in two directions. For example, let's say this object started at t is equals to 0 and t is equals to t1. This is the position of this object. Now it has two components. So this object, I can say this has some x component and this has some y component. So this is the y component of position and this is the x component of position. So this is the x-axis and this is the y-axis. So what is the position vector? As I said earlier, once again, you have to connect the origin with the final position of the object. So this is the position vector. So this is my position vector. So I can say this point is A and this point is B. So vector AV in this case is my position vector. In fact, I can write this position vector in terms of Cartesian coordinates and using the unit vector. You may remember when we discuss vector chapter, in the x direction we generally use unit vector I cap and in the y direction we use unit vector j cap. So this distance or this vector r is nothing but sum of x vector, that is xi, and y vector. So this is my x vector and this y is nothing but yj. So this is my bi-component vector. So if I want to calculate this vector, so this vector is nothing but sum of this vector plus this vector. So I can say vector r is nothing but sum of xi plus yj. So if I have a motion in two dimensions, I can denote position vector simply xi plus yj. Now what about if I have a motion in three dimensions? This is the extension of the previous case. Now you understand, if you have a motion in the three dimensions, you will have x component, y component and z component. And then how will you denote the position vector? You will basically denote the position vector as xi plus yj plus zk. So only one thing we are changing, that we are adding third component. To illustrate this, let us say I have an object and this is here at t is equals to 0 origin, and this is my x-axis, this is my y-axis and this is my z-axis. So these are the three axes. Unit vector along x-axis I, along y is j cap and along z this is k cap. Now at certain point of time this object has reached to this position, that is position P. So it has started from O origin and it reached to position P. So what is its position vector? As I said earlier, you have to connect the origin with the final position. So in this case, this is my position vector. Now I can write this position vector as sum of three vectors. First, if I take xi and yj, if I sum these two vectors, I will get a vector that basically passes through this plane. So this plane, you see, in this case we have a plane. So on this plane I have a vector that is this vector. This vector is nothing but xi plus yj. So xi plus yj will give this vector. Now if I sum further, so I basically sum this vector and this vector, I got a vector something like this, that is on plane xy. Now if I at z vector, that is zk, so this is my xi cap, this is by j cap, and this is zk cap. So if I add zj cap, I will basically have this vector, and that is nothing but xi by j plus zk cap. So I can say if I want to write position vector in 3 dimensions, I have to basically sum all the components with corresponding unit vectors. So now you understand, finding position vector is not a difficult task. What you have to do is, you have to simply first find the coordinates. What is the coordinates of that vector? That is x component, y component, and z component. This component, this component, and this component. Once you know these 3 components, you can write position vector, that is r vector. Now let us discuss about average velocity, and this will discuss in 2 dimensions. If you remember, in 1-dimensional video we discussed displacement, or the average velocity is nothing but displacement divided by time interval. That is, average velocity V average is equals to displacement, that is delta x, divided by time interval dt. That we learned in the previous chapter, that is in 1-dimensional motion. I can further basically generalize, since the motion is happening in 2 dimensions, it can also happen in 3 dimensions. We can replace this x with the position vector. That was basically position, x was position. So now what I can do is, I can replace this position vector. So now I can say change in position vector divided by time will give you the average vector. So this can be written here. Let's say I have an object. This object at t equals to 0 is here, and sometime t1, this is at position p1, so this is position at time t1, and this is position at time t2. So this is the position of object. Object is at position p1 at time t1 and at p2 at time t2, and I am interested to find what is the average velocity in this case. So what I will do is, first we will find position vector of p1. So what is that? Simply I have to connect the origin with the final position. So this is my position vector. That is r1 vector. That is position when the object is p1. Similarly, what is the position vector when the object is at point p2? So this is the position vector. When the object is point number 2, that is p2, that is vector is r2. So position vector is r2, and we put a arrow sign on the top to show that this is a vector. Now what we said average velocity is defined as change in displacement or change in position vector divided by time interval. So in this case, what is the change in position vector? So initial is r2, that is final is r2, and initial is r1. So we have to basically find change, that is r2 minus r1, and then we have to divide by the time interval. In this case, time interval is t2 minus t1. Now this term that is on the top, r2 minus r1, is nothing but change in position vector. So let us try to see this once again. Now this is r1 and this is delta r. So this is change in position. So if I use this triangle O, P1 and P2, I can write r1 plus delta r, and this is equals to r2 vector. So what I am using here? I am using sum of 2 vectors is equals to third vector, that is vector r1 and vector delta r, and if you sum these two, you will get the third vector, that is vector r2. So from here I can write delta r is nothing but r2 minus r1. So now I can plug this vector, that is r2 minus r1 is nothing but delta r. So r2 minus r1 is nothing but delta r, that is delta r vector. So, and this divided by delta t. So now I can write velocity, that is average velocity, is nothing but simply change in position vector, that is delta r divided by delta t. So in this case, this is the change in position vector, and then I have to basically subtract this. If I want to calculate delta r, I have to subtract r2 minus r1, that is subtract r2 and r1, and then divide by delta t, and then you will get the average velocity vector. So what about average velocity vector? Whether it's a scalar or it's a vector. You see, this is a vector quantity. Why this is so? Why this is so? Because we are calculating velocity average is nothing but change in velocity, change in position vector divided by time. So velocity average is a vector quantity. You see, what we are doing is we are simply multiplying delta r vector with 1 by delta t. So this is your average velocity. So what we are doing is we are multiplying delta r with a term 1 by delta t. So this is a vector quantity and this is a scalar quantity. So this is nothing but you are simply multiplying the change in position vector with a scalar quantity, and that's why the average velocity will be a vector quantity. So calculating the average velocity is simply change in position vector multiplied by a scalar coefficient. Now if you have a one dimension, things becomes easy. You simply write average velocity is equals to position x2 minus position x1, and is divided by t2 minus t1. Once again, this average velocity is in the x direction. Since I know the direction, that is in the x direction, we know this is a vector quantity. Now next we will discuss a term called instantaneous velocity, and this is related to average velocity. When you calculate the average velocity, you require two times, time t1 and time t2, and then you calculate the difference in time, that is change in time, delta t, time interval. Now this time interval can be very large, or it can be very small. So instantaneous velocity is basically limit of average velocity, limiting case of average velocity when delta t tends to 0. When delta t becomes 0, we define average velocity as instantaneous velocity. So it is the limit of average velocity as time interval approaches 0, it is equals to instantaneous rate of change of position with time. So instantaneous velocity is nothing but instantaneous rate of change of position with time. So when your time is very small, that is 0.0001 second or even less than that, in that case your average velocity becomes or tends to instantaneous velocity. So let us try to see using this figure. So this is position of object at time t equals to t1, that is p1, and corresponding vector is r1, and this is position at time t2, corresponding vector is r2, and in this case r1. So delta r, that is change in position vector, is nothing but r2 minus r1. So this point is here and this point is here. Now if I decrease delta t, what will happen? Sometime this point will be here, so p2 will be here. Depending upon time, if I take even a smaller, p2 will be here, p2 will be here. In that case, your delta r is becoming a smaller and a smaller. And a limiting case will come when this is very close to here, somewhere here. So this, in that case, delta r is only this much. So this is your r2 and this is your delta r. So your triangle is becoming a smaller and a smaller. So this is r1 vector, this is r2 vector, and this is delta r vector. So as time basically tends to 0, or you take a smaller and a smaller time, the change in position vector becomes smaller and smaller, and point P1 and point P2 are coming close to each other, and in those cases we define instantaneous vector, that is instantaneous velocity. So this is your average velocity. So this is the expression for average velocity. Change in position vector divided by time, that is time interval. And then this term, that is limiting delta t tends to 0. So limit delta t tends to 0. It's saying that now delta t is becoming a smaller and a smaller, then delta r is also becoming a smaller and a smaller. In that case, I can write very small change interval of time is dt. So dt is very fraction or a small fraction of change in time. And similarly, delta r or dr is basically very small change in position vector. So if I object here, so this is my position vector, and if this changes with very small amount of time, in dt time, if this changes by dr, then we define instantaneous velocity is equals to dr divided by dt. So you see, dr vector is becoming a smaller and a smaller. A time will come when point P2 and point P1 will basically coincide very close to each other. That point of time is basically your instantaneous velocity. So you can see, you can measure instantaneous velocity by taking delta t as small or even larger. So your accuracy will depend upon what is the value of delta t. If this is very small, in that case you will get exact instantaneous velocity. If the delta t value is large, in that case you will get relatively inaccurate, or result will not be that accurate in that case. So you have, if you want to calculate instantaneous velocity, your delta t or dt time should be a small. So as I said, instantaneous velocity is a vector quantity. So the magnitude of vector at any instant is the speed of particle at that instant. So what is the magnitude of instantaneous velocity? That is, you have to simply take magnitude of instantaneous velocity. That is nothing but what is the speed at which speed the object is moving. So instantaneous velocity is a vector quantity. It has two things. One is the speed, another is direction. That is magnitude and direction. So how do you calculate magnitude? So magnitude is simply a speed of the object. At what speed the object is moving at that point of time is called basically magnitude of instantaneous velocity. Similarly, the direction at any instant is same as the direction in which the particle is moving at that instant. So when we want to find what is the direction, then this is simply the direction of motion of particle, that is the instantaneous velocity direction. So if you want to find the direction of particle, so you have to see simply in which direction the object is moving, in which direction the particle is moving. That will give you the direction of instantaneous velocity. So to conclude, at every point along the path, the instantaneous velocity vector is a tangent to the path at that point. So this is important. As I said, if you basically choose point P2 very close to point P1, then you define instantaneous velocity. So if your point P2 is coming very close, because delta t or dt becoming a smaller and a smaller, what will the position? At this point, the object is moving in this direction, and this point is coming close and close. So this means in this direction, this is the motion of the object. So if you want to find the direction of instantaneous velocity, it is nothing but you have to simply make a tangent to the path. So if this is the path in which this object is moving, so this is the path along which this object is moving. If you want to find what is the direction at point P1, then you have to simply make a tangent. At point P2, what is the direction? You have to simply make a tangent. Any other point, you have to simply make a tangent. So tangent at the path will give direction of instantaneous velocity. Why this is so? Because point P2 and point P1 are coinciding. As they are coinciding, the direction of velocity is nothing but simply its tangent to the trajectory, tangent to the path is the direction of instantaneous velocity. For example, if this object is moving in this direction, so this is the path. If you want to find what is the direction at point P1, you have to simply make a tangent. So this is the direction. At this point, you have to simply make a tangent. So this is the direction. You see, direction is not constant in this case. At this point of time, this is the direction, and this point of time, this is the vertical direction. So direction is changing with time. So instantaneous velocity will have different direction. So that's why this is called instantaneous velocity. What is the direction? What is the magnitude and direction at given instant? So your magnitude is also changing and direction is also changing. So you have to give the at instant what is the magnitude and what is the direction. That is your instantaneous velocity. Now finally, we will see the instantaneous velocity in components in Cartesian coordinates. If you remember, the position vector r can be written as xi plus yj plus zk. This is the position vector r, and if I take derivative of the position vector, that is dr over dt, that gives you the instantaneous velocity. Now I can also write, so dr by dt is nothing but d by dt of xi plus yj plus zk. Now if you remember the rule of differentiation, so I have to sum and then differentiate. This is same as differentiate and then sum. So what I will do is, I will first differentiate the first term, then take the sum, then second term, take the sum, then differentiate the third term. So what we can do is, we can differentiate separately and then we can take a sum. That is here. So what we are doing is, we are first differentiating the first term. So dy dt of xi cap, and since I is a constant, I can take I outside. So this becomes simply dx by dt, or I can write dx by dt I cap. So this is my first term. Similarly, you will have other term. So dy by dt j cap and dz by dt k cap. I can write velocity vector vxi plus v by j plus vzk, and this is velocity vector. On the right side we have dx by dt I cap, dy by dt j cap plus dz by dt k cap. Now this is the expression for velocity in terms of Cartesian coordinate. So what we can do is, we can basically compare the I cap, j cap and k cap. So if you see on the right hand side, I cap term is vx, and so basically this is left hand side, and right hand side we have dx by dt. So I can write vx is equals to dx by dt. So this is my velocity. v by is nothing but dy by dt. If you compare this term and this term. Similarly, k cap, if you compare the coefficients of k cap, we can write vz is equals to dz by dt. So this means if you have a motion in 3 dimensions, you can calculate 3 velocity components separately. That is vx, you have to take the x component and then take differentiation. Z component, vz, calculate the z component of position vector and take the differentiation. So this makes life easier. You don't have to work with the position vector r. You can now work with Cartesian coordinate x, y, z, and it is easy to find Cartesian coordinates x, y, z. So what we are doing, you have a complex problem of finding the position vector, but now you are basically simplifying that problem in terms of x, y, z coordinate. So this is shown in this figure. So this is your position vector xi, this is yj, and this is zk. Similarly, if you want to find velocity vector, you will have 3 components, vxi, vyj and vzk. So what will the magnitude of position vector? You have to take simply a square root of vx square, vy square plus vz square. This you can basically understand. If you see this triangle, that is this triangle, this is the hypotenuse is nothing but x square plus y square under root. Now then you have to sum with this. So this is another vector, that is z vector, zk cap, If you consider this triangle and this triangle, this is again a right angle triangle because this angle is 90 degree. So this is nothing but this square plus this square, and then you have to take the under root. And this is nothing but z, and this is what? This distance is x square plus by a square. So this distance will become x square plus by a square. So this will be x square plus by a square plus z square, and then you have to take the square root. If you do the same thing with the velocity, you will get the magnitude of velocity vector, that is bx square plus by square plus bz square, and then you have to take the square root. So generally magnitude is written with this symbol. So we put two vertical lines, one left side, another right side, and that denotes the velocity, magnitude of instantaneous velocity. If you have only two-dimensional motion, Vz is 0, there is no component, there is no z component. In that case, we can simply calculate magnitude of velocity, that is Vx square plus Vy square. Finally, how we calculate the direction of instantaneous vector. So if I know I have a motion in 2 dimensions, this is x component of velocity and this is y component of velocity, and this angle is alpha. So this angle will give the angle of instantaneous velocity with the x component of velocity. So we can calculate in this triangle, you see this is Vy, then this is Vy, and this is Vx. So I can write tan alpha is equals to this component, that is Vy, and divided by this component, that is Vx. So this is my tan alpha. So we can calculate the direction of instantaneous velocity, that is at what angle the direction of instantaneous velocity is, by taking tan alpha is equals to Vy divided by Vx. So now I know magnitude of instantaneous velocity. In case of 2 dimensions, this is simply a square root of Vx square plus Vy square, and direction of instantaneous velocity, that is Vy divided by Vx. So we introduced two terms. One is average velocity, another is instantaneous velocity. Instantaneous velocity is more interesting term or generally used compared to the average velocity. So generally whenever we say velocity, this means instantaneous velocity. We hardly use term average velocity. So in next few chapters or next few problems, whenever we are saying velocity, this means instantaneous velocity. What is the velocity at that instant? What is the magnitude of velocity at a given instant? And what is the direction at that instant? That is basically instantaneous velocity. So in this lecture or in this video, we have seen what is position vector, what kind of motion we have in 2 dimensions, how we calculate position vector, how we calculate velocity vector, what is average velocity, what is instantaneous velocity, what is magnitude of instantaneous velocity, and what is the direction of instantaneous velocity. And I hope you enjoyed this video, and if you enjoyed, please share with your friends, and I will see you in the next video. Thank you. Hello friends. In the last video we have seen how to write expression for position vector, how to calculate average velocity vector, and how to write expression for instantaneous velocity. And this we have illustrated for 2-dimensional motion, that is if we have an object that is moving in a plane. Now we will support this video with the theory that we developed in the last video. So this problem says a robotic vehicle or rover is exploring the surface of Mars. The stationary Mars lander is the origin of coordinates and the surrounding surface lies in xy plane. So we have a robotic vehicle, often called rover, and this vehicle is trying to explore the surface of Mars. So a lander basically lands on the surface of Mars, and we have to consider this lander as a stationary Mars lander as the origin. So lander is the origin of coordinate system, and the motion of rover happens in xy plane. So this is a 2-dimensional motion. So we have to apply formulae concept for 2D motion. Furthermore, the question says the rover which we represent as a point has x and y coordinate that vary with time as follows. So we have to consider rovers as a point. So my rover is a point and this is moving in xy plane. So if it is moving in xy plane in 2D, it has two coordinates. It will have x coordinate and it will have y coordinate. So problem gives you the x coordinate and y coordinate which is as a function of time. So x coordinate is given by this expression and y coordinate is given by this expression. So now the first part of the question is find the rover's coordinate and distance from the lander at t is equals to 2 seconds. So we have to find position vector. And once I know position vector, I can calculate distance from the lander. And lander is basically in this case is origin. And we have to calculate this for t is equals to 2 seconds. But before that, let us analyze situation at t is equals to 0 second. So what is happening at t is equals to 0 second? So we can calculate x coordinate and y coordinate of rovers. So let us first calculate x coordinate. So we have the formula for x coordinate. So this is the formula. So we have 2.0 meter minus 0.25 meter per second square and t is equals to 0 I have to plug. So this is 0 second and this is a square. So this is basically 2 meter. Now similarly I can calculate y coordinate. And the y coordinate is given by this expression. If you see, this y coordinate has multiplied by time. Both term in this y coordinate is multiplied by the time. And time is 0. This means this term is 0 and this term is 0. This means y coordinate is 0. So at t is equals to 0, the x coordinate is 2 meter and y coordinate is 0 meter. So this is the coordinate at t is equals to 0 of the rovers. So once I know the coordinate, I can basically write the position vector. So position vector at t is equals to 0, let's write r0 vector. So this is nothing but xi and x in this case is 2 meter and the unit vector along the x-axis that is I cap plus y component that is 0 meter and unit vector along the y-axis that is j cap. So this is the position vector at t is equals to 0 second. Now let us find position vector at t is equals to 2 second. So how will you find? Once again you will use the same expression. Only thing is now in place of time you have to plug t is equals to 2 second. So this is 2 meter minus 0.25 meter per second square and this multiplied by t square, in this case t is 2 second and then this is a square. So if you calculate this value will be 1 meter. Similarly I can calculate y coordinate, that is 1.0 meter per second times t is nothing but 2 second and then plus, so this is here 0.025 meter per second cube and this multiplied by 2 second raised to the power 3. So if you calculate, this value will come 2.2 meter. So now I know the x coordinate and y coordinate at t is equals to 2 seconds. So x coordinate is 1 meter and the y coordinate is 2.2 meter. So I can write position vector at t is equals to 2 seconds. So let's write r2 vector. So this is position vector at t is equals to 2 seconds. So this will be x component, that is 1 meter multiplied by the unit vector I cap plus y component, that is 2.2 meter multiplied by the unit vector, that is j cap. So now I know the unit vector at 2 seconds, that is a position vector at 2 seconds. We can show all this using a diagram. So let's say this is y-axis and this is x-axis. So at t is equals to 0, what is the situation? At t is equals to 0, x is 2 meter and y is 0 meter. So we have somewhere here. So this is 2 meter and the y is 0 meter, and this is origin. So this is the position, that is t is equals to 0 second. Now what is the position at t is equals to 2 second? X is 1 meter and y is 2.2 meter. So somewhere here. So this is 2.2 meter and this is 1 meter. So this point is somewhere here. So this point is at t is equals to 2 second. So what is the position vector? If you remember, position vector is nothing but you have to make a line from origin to the final position. So this is the position vector at time 0, that is r0. And this is the position vector at time t is equals to 2 second, that is r2 vector. So these are the position vector, that is the position of the object corresponding to 0 second and corresponding to 2 second. So questions ask, what is the distance from the lander at t is equals to 2 second? So this is the distance. So this distance we have to calculate, that is magnitude of r2 vector is the distance of the rover from the lander. So this is my lander. So lander is here and rover is here. And this is the distance. So this is the position vector. If I take the magnitude of the position vector, that will give me the distance of the rover from the lander. So I have to take magnitude of r2 is nothing but 1 meter I cap plus 2.2 meter, and this is j cap. So I have to take the magnitude of this. So this will be a square root of 1 meter square plus 2.2 meter square. So if you calculate, this will come 2.4 meter. So at t is equals to 2 second, the rover is at a distance of 2.4 meter from the lander. And what are the coordinates? Coordinates is x coordinate is 1 meter and the y coordinate is 2.2 meter. So this is the coordinate and this is the distance of the rover from the lander. This is part 1. Now the second part of the problem says, find the rover's displacement and average velocity vector for interval t is equals to 0 second to t is equals to 2 seconds. So we have to calculate two things. We have to calculate the displacement and average velocity between t is equals to 0 second to t is equals to 2 seconds. How will you calculate displacement? If you remember, displacement or change in the position vector basically denotes the displacement, and in this case r2 is the position vector at point t is equals to 2 second minus r0, that is the position vector at time t is equals to 0. That will give me the displacement, that is the change in the position vector gives you the displacement. And you know what is the value of r2. This is the value of r2, and we know similarly value of r0 vector. So if I plug these two, we can calculate change in the position vector. So we can write r2 is equals to 1 meter I cap plus 2.2 meter j cap, and this minus 2 meter, this is I cap, and j component was 0, so 0 j cap. So if you calculate this, this will come minus 1 meter I cap, that is minus 1 meter I cap plus 2.2 meter j cap. So this is the change in displacement or change in the position vector that will give you the displacement of the rover. So this is the displacement of the rover. So we can also show this displacement in the same graph. So if you see, in this case, this one, that is from here to here, this denotes delta r, that is change in the position vector or the displacement. So this is the displacement. Now we have to calculate average velocity. So if you remember, average velocity is defined as, what is the formula for average velocity? So average velocity, if you remember from the last class, average velocity is nothing but change in position vector, that is displacement, divided by time interval. This is your average velocity. So we calculated change in position vector, that is minus 1 meter I cap plus 2.2 meter j cap, and this divided by, because we are calculating average velocity between 2 second and 0 second. So this is 2 second minus 0 second. So this will be minus 0.5 meter per second I cap. So this is I cap, and plus 1.1 meter per second. So this is 1.1 meter per second j cap. So this is the average velocity we will have between t is equals to 0 and t is equals to 2. So we can also write the same thing, V average is equals to, now this is also a vector. Velocity average is a vector quantity, and the value of this is minus 0.5 meter per second I cap plus 1.1 meter per second, and this is j cap. So this is the velocity vector or average velocity vector between t is equals to 0 and 2 second. So in terms of Cartesian coordinate, I can say velocity vector has two components. One is Vx and another is Vy, and Vx is nothing but minus 0.5 meter per second, and Vy is nothing but 1.1 meter per second. So object has two components, that is rovers has two component of velocity, x component as well as y component. This means this is example of 2D motion. So rover is moving in a plane. Now finally the third part, find the expression for rover's instantaneous velocity vector v, and express v at t is equals to 2 seconds in component form and in terms of magnitude and direction. So we have to calculate the instantaneous velocity, expression for instantaneous velocity, and then we have to calculate what is the velocity at t is equals to 2 seconds. We have to express my answer in terms of component as well as magnitude and direction. Now how will you do that? So if you remember, in the last class we said, if you want to calculate Vx, you have to simply differentiate x with respect to time. So this will give you Vx, that is dx by dt. Of course, in this case also, this is a vector quantity. Since I am writing in the x direction, there is no need to put this as a vector because now I am writing in the x direction. Similarly, Vy I can calculate if I take the differentiation of y with respect to time. So let us take differentiation of this term, that is x, and we can calculate Vx. So Vx is equals to, differentiation of this constant is 0 and this is minus 0.25 meter per second square, and then I have to multiply by 2t. Differentiation of t square is 2t. If you remember, there is a formula, x raised to the power n, differentiation of that is nx n minus 1. So I am using that formula. So if you use that, this will come minus 0.5 meter per second square and then multiplied by time. So this is the Vx. Similarly, I can calculate Vy, which is nothing but dy by dt. So I have to differentiate by component. So this one. So we will have 1 meter per second and differentiation of t is simply 1, and this is 0.025 meter per second cube, and differentiation of tq is 3t square. So I can write 1 meter per second plus this is 0.075 meter per second cube, and this multiplied by t square. So this is Vx and this is Vy. So once I know Vx and Vy, I can basically write V. V is nothing but Vx I cap plus Vy j cap. So Vx in this case is minus 0.5 meter per second square t, and then I have to put I cap here and then plus this term, that is 1 meter per second plus 0.075 meter per second cube t square. So this is t square and this is j cap. So this is your velocity. So now I know the velocity and it is in the two direction because Vx component is there and Vy component is also there. So we can calculate this velocity at different instant. For example, in this program it is said that we have to calculate this velocity at t is equals to 2 seconds. So let us plug t is equals to 2 seconds. So if you calculate this velocity at 2 seconds, so this will be, so here I will have minus 0.5 meter per second square and time will be 2 seconds in this case, and this multiplied by the I cap plus 1 meter per second plus 0.075 meter per second cube, and time is 2 seconds, so 2 seconds square, and this all is multiplied by j cap. So this all is multiplied by j cap and I cap. So if you calculate all this, this will come, the x component will come minus 1 meter per second I cap, and the y component will come 1.3 meter per second, and that is basically j cap. So now I know the velocity vector. This is the instantaneous velocity at t is equals to 2 seconds. So what we did, we basically calculated an expression for velocity, instantaneous velocity, and once I plug the value at different point of time, we can get the value for instantaneous velocity or vector for instantaneous velocity. So this is the instantaneous velocity vector at t is equals to 2 seconds. So once I know the vector, I can calculate a speed, that is magnitude of instantaneous velocity. So this is simply nothing but a square root of x component, that is minus 1 meter per second square, plus y component, that is 1.3 meter per second, and then I have to take a square of this, and then finally if you take all this and then take the root, this will come 1.6 meter per second. So the speed or instantaneous speed at t is equals to 2 seconds is basically 1.6 meter per second. Now you can see the velocity has one component that is negative, another component that is positive. So we can show this in this graph also. So this is my x-axis and this is my y-axis. So initially the robber was here, and finally at t is equals to 2 seconds this robber is here. So what is the velocity at t is equals to 2 seconds? So this point corresponds to t is equals to 2 seconds. So it has a component, velocity component, the x component is negative, so this has in this direction, and the Vy, that is positive, so this direction. So what is the resultant velocity? So resultant velocity will come in this direction. So this is Vy and this is the resultant velocity. So we can basically calculate what is the angle that the resultant velocity makes with the positive direction of the x-axis. And if you remember in the previous class or previous video, we discussed tan alpha, where alpha is the angle from the positive direction of the x-axis, is nothing but Vy divided by Vx. So Vy in this case is 1.3 and Vx is minus 1. So this means I can write tan alpha is equals to minus 1.3. So from here you will get alpha is equals to minus 52 degree. Minus 52 degree, this means positive, this is a negative, so this is negative angle, So if you want to convert this into the positive angle, then you have to basically subtract from 180. So this is the negative angle. Equivalent to this angle, corresponding positive angle will be 180 minus 52 degree, that is 128 degree. So this means this vector is making an angle of 128 degree from the positive direction of the x-axis, or the same thing I can say this vector is making an angle of minus 28 degree, minus 52 degree, that is the negative side. This is minus 52, so this is the angle minus 52 I can say, or I can say this vector is making an angle of 128 degree from the positive direction of x-axis. Same thing, either you measure the angle from positive direction of x-axis or you give answer in terms of negative, but in that case you have to measure from the negative direction of the x-axis. So we calculated the magnitude of velocity and we also calculated the direction of the velocity. So when we have instantaneous velocity, there are two important things. What is the magnitude? Magnitude in this case is 1.6 meter per second. What is the angle? That is 128 degree is the angle in this case. If you try to compare, if you remember, we calculated average velocity between 0 and 2 seconds, and that was V average is equals to minus 0.5 meter per second I cap plus 1.3 meter per second J cap. You can rewind the video and you can see this expression that we calculated. And the instantaneous velocity, so this is average velocity vector, and the instantaneous velocity at t is equals to 2 seconds that we just calculated, that is nothing but minus 1 meter per second I cap plus 1.3 meter per second J cap. So you see basically this was 1.1, not 1.3. So you see the average velocity is not same as the instantaneous velocity. Here average velocity and instantaneous velocity are different, not only the total, even in terms of each component. Vx of average velocity and Vx of instantaneous velocity are not same. Similarly, Vy of average velocity and Vy of instantaneous velocity is not same. So this illustrates that average velocity and instantaneous velocity are two different things and they will not be equal. So in this video, we explained through a problem how do you calculate position vector. How do you calculate change in the position vector? How do you calculate average velocity vector? And finally, how do you calculate expression for instantaneous velocity? And instantaneous velocity has a magnitude as well as angle, and we can calculate using the formula both the magnitude as well as the direction of the instantaneous velocity vector. And I hope you enjoyed this video, and if you enjoy, please share with your friends, and I will see you in the next video. Thank you. Hello friends. In the last video we have seen how to calculate average velocity, and we have also seen how to calculate instantaneous velocity of an object when this object is moving in two dimensions. That is, if the object is moving in a two-dimensional plane. Now in this video you will see how to calculate acceleration vector. Now the first question is, what is acceleration? So acceleration basically describes changes in particles' velocity. Now velocity is a vector quantity. It has magnitude and it also has direction. So when I say change in velocity, this means it can change in magnitude or it can change in direction. So when there is a change in velocity vector, then we say there is a acceleration. Now three possibilities are there. The magnitude of velocity can change, or direction of velocity can change, or magnitude as well as direction both can change. So in all these situations we will say that body is accelerating. So if the speed increases, generally we call this as an accelerating object, and if a speed decreases with time, we call this as a decelerating object. So in short, we can say acceleration describes how the velocity of the particle changes with time. To discuss further, let us consider a moving car. And this is the car. And this car initially, let's say this is the position of the car at t is equals to t1. And this car is moving with a velocity v1. So velocity has a magnitude as well as direction. So direction is shown, and this is the direction of velocity when the particle is at point p1. Now see, this particle is moving in a curved path. So this car is moving in this curve. So after some point of time, this car has reached to this point, that is point number P2. And the velocity direction has changed. Initially, the direction of velocity was in this direction. Now the velocity direction is in this direction. So there is a change in the direction of velocity because this is moving on a curve, and curve is changing the path. So velocity direction is also changing. We can also think of this car is changing its magnitude of velocity also. So magnitude of velocity is also changing as well as direction is changing. So this is an accelerating car. So we can say this car accelerates by slowing while rounding a curve. Its instantaneous velocity changes in both magnitude and direction. So this car is trying to take a turn on this curved path. So this is trying to slow down. So its velocity, magnitude, that is basically speed, and direction of velocity both are changing. So this is an accelerating car. We can say instantaneous velocity, magnitude and direction both are changing. Now to derive some mathematical expression, we will do the same thing in a different graph. So this figure, the same figure, so this is the curved path we have in which this car is moving, and this is point P1 where this is the direction of velocity, and this is point P2 where this is the direction of velocity. Now if you remember, there is a rule that you can translate or freely move a vector parallel to its initial position. So what we are doing is, this is initial vector v1, so we are basically translating this vector v1. So this vector has translated, and now finally, so this is after translation. So finally this is the position of vector v1. So this is vector v1 after the translation. Now similar thing I can also do for v2. So I have to basically translate v2 parallel to its initial direction. So let's make this line and this line that is perpendicular to v2, and then translate v2 in this direction. So this is the translation in which direction we are translating to v2. So finally if I translate this, I will have v2 somewhere here. So now we have translated v1 and v2. This means now this is the position of v1 and this is the position of v2 after the translation. Important point, when we are translating the two vectors, we are trying to merge the tail part of the two vectors at the same point. So we have translated and we try to merge the tail so that the tail remains at the same point. So this is my vector v1 and this is my vector v2. Now this vector that is joining v1 and v2 is basically change in velocity vector, that is delta v. We can calculate this vector basically. So let's call this vector as delta v. So we can write in this triangle v1 plus delta v is equals to v2. That is the rule of vector, triangle law. So if I use triangle law, I can write v1 plus, v1 is a vector, delta v is a vector, v1 plus delta v is equals to v2. So from here I can write delta V is nothing but V2 minus vector V1. So this is what here I have, that is V2 minus V1, vector V2 minus vector V1 denotes the change in the velocity vector. So you see how we calculated change in the velocity vector. So first I freely translated vector V1, translated vector V2 so that the tail coincides, and once I have the coincidence of tail, what we can do is we can make the third vector, that is delta V. So this is the third vector that we are making, and then we can use triangle law and we can calculate magnitude of delta V. So in this case magnitude of delta V, that is change in the velocity vector. It includes the direction change, it includes the magnitude change, because this is a velocity vector, change in the velocity vector. So this is equals to V2 minus V1. Now if I divide change in velocity vector delta V with time, I will get acceleration. Now which time I should take? I can take time interval, that is t1 to t2, and in that case we will calculate average acceleration. If this time interval is very small, in that case we are calculating the instantaneous velocity or instantaneous acceleration. So let us first define average acceleration. So average acceleration is defined as change in velocity vector divided by time interval, that is delta V. So I can define average acceleration. So this is average acceleration is equals to change in velocity vector divided by time interval delta t. As I said, delta V is nothing but V2 minus V1, so I can write V2 minus V1, and change in time, this is T2 minus T1. So I can write velocity vector A average is equals to V2 minus V1 divided by T2 minus T1. That is same as delta V divided by delta T. So this is the average acceleration vector. Important point, this vector, average acceleration vector, is a vector. It's not a scalar quantity. If you see this term can be thought as 1 by delta t multiplied by delta v. So this is a vector quantity, and this vector quantity is multiplied by some scalar number. 1 by delta t is nothing but a number. So direction of average acceleration is same as direction of change in the velocity vector. This I can further illustrate using this diagram. So this is the same diagram that I showed just. So this is position at time t1, this is position of car at time t2, and this is the velocity vector at time t1, and this is the velocity vector at time t2. And as I said, I can translate this vector and I will have v1 vector. Similarly, I can translate this vector and I will have v2 vector, and this is basically change in velocity vector, that is v2 minus v1. So see, what is the direction of change in velocity vector? So this is towards the center of this curve. So if you consider this curve, so center of this curve will be somewhere this side, that is inside. So the direction of velocity vector or change in velocity vector in this case is towards the center of this curve. So, and also the average acceleration will be in the same direction. So this is the direction. So this is the direction of change in velocity vector, and this is the direction of average vector, average acceleration vector. Because average acceleration is nothing but delta b divided by delta t, and the direction of average acceleration is same as change in velocity vector. So we can say average acceleration is a vector quantity in the same direction as the vector delta v. So average acceleration has same direction, that is the change in velocity vector. Now we have written expression for average acceleration, a general average expression. Can you write same thing only for x direction? So you have to write expression for average acceleration when object is moving in x direction, that is a straight line, 1D motion. So in that case I can write average acceleration in the x direction is equals to change in velocity in the x direction divided by delta t. Similarly, you can write average acceleration in the y direction, z direction, and then you can basically all club together, then you can get the average acceleration in terms of Cartesian coordinate. Now next concept we have instantaneous acceleration. So what is instantaneous acceleration? So when we say instantaneous acceleration, the meaning of this word, that is acceleration at an instant, that is instantaneous acceleration. So this is a special case or limiting case of average acceleration. So if you take time t1 and t2 very close to each other, then we can define instantaneous acceleration. So this is instantaneous acceleration. A is a vector quantity at point p1 as the limit of average acceleration vector when point p2 approaches point p1, so delta v and delta t both approaches to 0. So let us try to illustrate this. First we'll illustrate for a curved path and then we will illustrate for a straight line path. So how we can calculate instantaneous acceleration when the object is moving in a curved path. So this is the same car that is moving in this curved path at point p1. So this is point p1. This is the velocity vector. In this case, velocity vector is v1. At point p2, this is the velocity vector, that is v2. So these two are instantaneous velocity at point p1 and point p2. What is my target? My target is to calculate instantaneous acceleration. So as I said, if I want to calculate instantaneous acceleration, what I have to do is I have to shift p2 towards p1 so that the distance between p2 and p1 is very small. Or in other words, time interval between two instants is very small. So what we do is we take limit of average acceleration when delta t goes to 0, and this can be written here. So instantaneous acceleration is equals to limiting case of delta v by delta t, that is average acceleration, when delta t tends to 0. So when delta t tends to 0, the average acceleration basically gives the instantaneous acceleration. And instantaneous acceleration is written as simply dv by dt. So when we have delta t very small, that goes to 0, delta v by delta t we can write as dv by dt, something like this. So now I can use calculus to differentiate the v function and I can get the instantaneous acceleration. So what will happen if you move p2 to p1? Basically in that case average acceleration will reach to instantaneous acceleration. So we take limit of average acceleration as p2 approaches to p1. So p2 is approaching to p1, and in this case whatever with the value of average acceleration, we'll call this as a instantaneous acceleration. And if you remember, the direction is towards the center, so this will be the direction of average acceleration, and when this reaches to 0, this time interval reaches to 0, this will also be direction of instantaneous acceleration. So this means that if delta v and delta t approaches to 0, we can say instantaneous acceleration is equals to limiting case of delta v by delta t when delta t goes to 0, and we will write simply dv by dt. Important point in this case, acceleration point to the concave side of the path. So this is towards the center, towards the inner side of the curve. So whenever we have a curved surface, so motion is happening along a curved path. In that case, acceleration vector or instantaneous acceleration vector point towards the concave side of the path, that is towards the inside of any turn that the particle is making. So if it is making any turn, then the acceleration vector is towards the inside of that turn. So this is when the object is moving in a curved path. So we can calculate acceleration vector or instantaneous acceleration vector when the object is moving on a curved path. Now similarly, if the object is moving in a straight line path, we can calculate the acceleration vector. So next situation, when the object is moving in a straight line trajectory. Same thing, this point P1, this is a car at time T1, velocity is V1, and this is along this. So this is the path on which this car is moving. So straight line. After some time, this is P2 and corresponding velocity is V2, and this is along a straight line. So you see in this case, the direction of velocity is constant. It's always along the straight line. Initially, this is in the straight line, and finally this is also in the same direction. So if I take the change in velocity vector, it will only change in magnitude. It will not change in direction. So when I calculate instantaneous acceleration, the direction of instantaneous acceleration is along the direction of motion, that is along the straight line. For example, in this case, V2 is in this direction, V1 is in this direction, so delta V will be in this direction. And similarly, acceleration will also be in this direction, because instantaneous acceleration is nothing but a scalar multiplication of change in velocity vector and when delta t goes to 0. So acceleration vector will have same direction as the change in velocity vector. So in this case, when the object is moving in a straight line, we will have change in velocity vector and instantaneous acceleration all along the straight line, all along the path, all along the trajectory, and in this case trajectory is a straight line. So if you have a curved motion, acceleration vector will be towards the inside, towards the center, but if you have a straight line, it will be along the straight line. So instantaneous vector can change its direction depending upon what kind of path you have. If you have a curved path, it will be inside the curve. If you have a straight line, it will towards the straight line. So acceleration vector may or may not be tangent path. So it can be tangent. For example, in case of a straight line motion, we can say the acceleration vector is tangent to the path. But when you have a curve, in that case acceleration vector is not tangent at the path. It's in contrast to the velocity. So when you calculate average velocity is tangent to the path. Instantaneous velocity is tangent to the path. Not the average velocity is tangent to the path. Instantaneous velocity is tangent to the path. But here, instantaneous acceleration can be tangent to the path or it may not be tangent to the path, depending upon in what kind of curve or in what kind of trajectory the motion is taking place. So instantaneous vector is an important concept. So when you are using instantaneous acceleration, generally when we say acceleration, this means instantaneous acceleration. So we never use average acceleration. Generally we use instantaneous acceleration. So when we are saying instantaneous acceleration term, this means instantaneous acceleration. Now how we can write instantaneous acceleration in Cartesian coordinate? So we'll see how we can write instantaneous acceleration in Cartesian coordinate. So as I said, I can write acceleration is equals to dv by dt. So acceleration is nothing but dv by dt and v is the velocity. Now I can write velocity something like this: vx I cap plus v by z cap plus vz k cap. That is, in Cartesian coordinate I can write velocity something like this. Now if I take differentiation of velocity, I will get the instantaneous acceleration. So let us take differentiation of this. So if I take differentiation of this will be dy dt of vxi plus vyj plus vzk. Now we can take differentiation of each term separately. So what I will do is I will write dy dt of vx, and this constant term I, so there is no point of taking the differentiation, so I can take outside. Similarly dv by y dt, and then I have to multiply by the unit vector j, and this is dvz by dt, and this is unit vector k. Now once I know this acceleration, I can basically equate. Acceleration will also have three components: ax component, a y component, and az component. So this is what? So this is acceleration. I can write acceleration has three components: ax I cap, ay j cap, az k cap. Now this will be equals to dvx by dt. So here I have dt, and this is I cap dvy by dt, and this is j cap and dvz by dt, and then we have k cap. Now we can equate I cap this side and I cap this side. So this is ax and this is dvx over dt. Similarly I can equate ay and az, and then in that case I will get these three different expressions. So this basically says how we can calculate three components of acceleration, that is ax, ay and az. Simply I have to differentiate the x component of velocity vector, y component of velocity vector, and z component of velocity vector. So if I want to calculate the component of acceleration, I have to differentiate the component of velocity vector. Acceleration is also related to displacement, or you can say position vector. So I can write, if you remember, I can write, first let us write velocity. So if you remember velocity, I can write, this is nothing but differentiation of position vector, and this is instantaneous velocity, and this I can write r is nothing but x I cap by j cap and z k cap, this divided by dt. So I can write velocity is equals to dx by dt I cap dy by dt j cap plus dz by dt k cap. So now I know expression for velocity. So vx I can equate, because I can write v is equals to vxi plus vyj plus vzk, and then if I equate, then I can get vx is nothing but dx by dt, and vy is nothing but dy by dt, and vz is nothing but dz by dt. And what is my acceleration? So if you remember, the x acceleration is here, that is dvx by dt. So if I take differentiation of this term, I will get acceleration in the x direction. So if you take differentiation of this, what will happen? X direction acceleration ax is nothing but dvx by dt, but vx is what? Vx is nothing but dx by dt. So vx is nothing but dx by dt. So I have to differentiate x first time, and then I have to differentiate it again. So I can write simply d2x by dt square. So now I have an expression in which acceleration is directly related to position vector, in this case only x direction. So we can write ax is equals to d2x by dt square. If I do the same thing for other components, I can write ax is equals to d2x by dt square, ay is equals to dt by dt square, and similarly I can write expression for az. And if I know the components of acceleration, I can write the resultant acceleration. So what is resultant acceleration? So resultant acceleration is axi cap ayz cap plus az k cap. So if I put the value here, this one, and this one, so ax is nothing but d2x by dt square. Similarly, ay and az, I get an expression of instantaneous acceleration in terms of different components, that is x component, y component and z component. So in this video we have seen what is average acceleration and how this is related to instantaneous acceleration. Basically, instantaneous acceleration is a special case of average acceleration when delta t goes to 0 or the 2 points are very close to each other. P1, P2 are very close to each other. In that case, we can define limiting case of average acceleration is equals to instantaneous acceleration. We also said the direction of instantaneous acceleration may be tangent to the trajectory or may not be tangent to the trajectory. This is in contrast to the velocity vector, instantaneous velocity vector. Instantaneous velocity vector is always tangent to the trajectory, but instantaneous acceleration is not like that. Now we also said how to write expression for instantaneous acceleration in Cartesian coordinate, and in that case you have to write a is equals to axi plus a by z plus azk. And finally we related the acceleration vector with position vector, and we said if you take the double derivative of the position vector, then it gives you the instantaneous acceleration vector. In one direction, you can say simply d2x by dt square is equals to ax. So I hope you enjoyed this video, and if you like this, please share with your friends. Thank you. Hello friends. In the last video, we discussed the theory for calculating the average acceleration and instantaneous acceleration. And that was for two-dimensional motion. That is, if motion has two components of velocity, Vx or Vy, then how we calculate these two terms, average acceleration and instantaneous acceleration. Now we will try to illustrate that theory using a problem in this video. And this problem we have already seen when we are doing calculation of average velocity and instantaneous velocity. So this is the same problem, but now we are going to calculate average acceleration and instantaneous acceleration. So problem says a robotic vehicle or rover is exploring the surface of Mars. The stationary Mars lander is the origin of coordinates and the surrounding surface lies in xy plane. So we have a robotic vehicle, and this vehicle is called rover, and this is trying to explore the surface of Mars. This robotic vehicle is moving in a plane surface, that is, motion is in two dimensions, and the origin of coordinate lies with the lander. So on Mars we have lander, so this is a stationary Mars lander we are calling. So this is the origin of this system. So on the coordinate system, on the origin we have a stationary Mars lander, and this robot, the rover, is moving in a two-dimensional plane, particularly the xy plane. Furthermore, the question says the rover, which we represent as a point, has xy coordinates that vary with time, and the x coordinate is given by this expression and y coordinate is given by this expression. So rover, we have to assume that rover is a point mass, and its x coordinate and y coordinate is given by these two expressions, and these two expressions depends upon time. So for different time period, you can calculate what is the value of x and what is the value of y using these two expressions. Now the first part of the question, find the component of average acceleration for time interval of t is equals to 0 second to t is equals to 2 second. So we have to calculate components of average acceleration. This means we have to calculate x component of average acceleration and y component of average acceleration. And this we have to consider for a time 0 to 2 seconds. So how will you do this problem? If you remember, the acceleration, for example, in the x direction, average acceleration in the x direction can be written as change in velocity in the x direction divided by the time interval. Similarly, acceleration in the y direction, that is average acceleration in the y direction, we can write delta Vy divided by delta t, where delta is the time interval and delta Vy is the change in the velocity. So I have to calculate what is the velocity at t is equals to 2 seconds and what is the velocity at t is equals to 0 second, and then I can calculate delta Vx, and then if I divide by delta t, I can get the average acceleration in the x direction, that is x component of the average acceleration. Similarly, I can calculate y component of average acceleration. So this means I have to first calculate velocity. So what is the x direction velocity? And this can easily be calculated because I know the position, x position of the rover. So if I differentiate this, I can get the velocity in the x direction. So x is given. So x is equals to 2 meter minus 0.25 meter per second square, and this is t square. Now if I differentiate, I can write dx by dt, and that is nothing but Vx. Constant term differentiation 0, and this is 0.25 meter per second square, and differentiation of t square is 2t. So this will be minus 0.50 meter per second square times t. So this is the velocity in the x direction. Similarly, I can calculate velocity in the y direction, that is dy by dt, and this is equals to Vy. So if you differentiate this, I will have 1 meter per second. So this is 1 meter per second, and differentiation of t is 1, and this is 0.025 meter per second cube, and differentiation of tq is 3t square. So if I rewrite this term, I will have 1 meter per second plus, and this becomes 0.075 meter per second cube, and this multiplied by the t square. So now I know the x component of the velocity and the y component of the velocity. So we can calculate what is the velocity at t is equals to 0. So let us calculate t is equals to 0. So what is the x component? This is, if I plug in this expression t is equals to 0, this becomes 0. What is Vy? Vy, this term, that is this term will be 0. No, this term will not be 0. This term will be 0 because we have t square. So we will have Vy is equals to 1 meter per second. Similarly, I can calculate velocity corresponding to t is equals to 2 seconds. So Vx, what will be this value? So this term multiplied by 2. So 0.5 into 2, that is basically minus 1 meter per second. What is Vy in this case? This term multiplied by 2, that is not 2, that is 2 raised to the power 2. So this will be, what will the Vy? I can write 1 meter per second plus 0.075 meter per second cube, and this multiplied by 2 seconds raised to the power 2. So if you calculate this term, this will come 1.3 meter per second. So this is 1.3 meter per second. So now I know Vx and Vy corresponding to t is equals to 0 and t is equals to 2 seconds. I can calculate acceleration, that is average acceleration. So this is V2 minus V1 divided by T2 minus T1, that is delta V divided by delta T, and in the x direction. So what is the velocity in the x direction at 2 seconds? So this is minus 1 meter per second. So this is minus 1 meter per second. What is V1? So this value is 0. So you can see here, so this is 0 meter per second. What is the time difference? So we have 2 seconds minus 0 second. So this will be minus 0.5 meter per second square. So this is the acceleration in the x direction. Similarly, I can calculate average acceleration in the y direction. That is v2 in the y direction minus v1 in the y direction divided by t2 in the y direction minus t1 in the y direction. Basically, this is not y direction. Time has no direction. So this is simply t2 minus t1. So what is v2? v2 in this case we have, this is 1.3 meter per second. Minus what is v1? That is 1 meter per second. So this value is 1 meter per second. And this divided by 2 second minus 1, so 0 second. So this is how much? So if you calculate this, this will come 0.15 meter per second, a square. So this is the average acceleration in the x direction and in the y direction. So you see, to calculate the average acceleration, what we have to do? We have to first calculate the instantaneous velocity, that is velocity. Instantaneous velocity is simply called as velocity. So we have to calculate the velocity. Expression for the velocity. Once I have the expression for the velocity, I can calculate the velocity for any given point of time. And once I know this velocity for different times, I can simply calculate acceleration, that is the dv by dt. So dv I know, that is v2 minus v1, dt I know, that is t2 minus t1. So this is about calculation of average acceleration. Now next we will discuss how we can calculate instantaneous acceleration. So we have to calculate instantaneous acceleration at t is equals to 2 seconds. So what is instantaneous acceleration? So if you remember, instantaneous acceleration, for example, let us say if I say x component of instantaneous acceleration, so this is nothing but, this is a limiting case when delta t tends to 0 and this delta v divided by delta t. And this can simply be written as dv by dt. And if I am calculating in the x direction, so I can write dvx. So dvx by dt, that will give me the instantaneous acceleration in the x direction. So the term vx we already calculated in the first part. If you remember, we calculated the vx. So what was the expression for vx? Vx is equals to, this was minus 0.05 meter per second square, and this multiplied by time. So that was the expression for Vx. Similarly, I remember the expression for Vy that we also calculated in the first part. So Vy was 1 meter per second plus 0.075 meter per second cube t square. So this was the expression for Vx and this was the expression for Vy that we calculated in the first part of the problem. So now we will use these two expressions to calculate Ax and Ay. So let us calculate Ax. So I have to simply differentiate this term. So this will be minus 0.05 meter per second square, and differentiation of t is simply 1. So this will be the x component of acceleration. Now if I differentiate v by with respect to time, I will get a by. Now this is a constant term, differentiation of constant is 0, and then this will be 0.075 meter per second cube, and t square, the differentiation for t square is simply 2t. So now I can write v by, that is a by, is nothing but this will be 0. So this is 15 meter per second cube into time. So we calculated the two components of acceleration. So this is the first component and this is the second component of acceleration. Basically now I can write this acceleration in a combined acceleration vector. I can write because I know the component, x component and y component. If you remember the acceleration vector, we can write simply axi cap plus a by j cap. So I can write using this expression. So a will be in this case simply ax is minus 0.05 meter per second square, and this is I cap, and plus this will be 0.15 meter per second cube t, and this is j cap. So this is y component and this is x component of acceleration. We have to calculate instantaneous acceleration at t is equals to 2 seconds. So let us plug t is equals to 2 seconds in this expression. So I will get this term will remain same, that is minus 0.05 meter per second square, and this is I cap, and this term will be, so if you put t equals to 2, this will become 0.30 meter per second square because 1 second cancels out, and this will be j component of the acceleration, that is the y component of the acceleration. So this is the acceleration vector that we will have. Now acceleration vector, instantaneous acceleration vector has two things. One is magnitude, another is direction. So basically we can find magnitude as well as direction both. So if you remember, magnitude of acceleration is simply ax square plus a by a square, and then you have to take the root, a square root of this. So in this case this value will be, this ax is nothing but minus 0.05 meter per second square. So square of this term plus 0.30 meter per second square, a square of this term, and then take the root of all. So this will come 0.58 meter per second square. So this is the magnitude of acceleration at t is equals to 2 seconds. Now we have to also find what is the direction of this acceleration, in which direction this acceleration is directed. If you remember, it was said in the beginning of the problem, so this is origin, that is the stationary lander position, and rover is somewhere, let's say here at t is equals to 2 seconds. It has two components of acceleration. One component is in the x direction, so this is my x axis, this is my y axis. So x component of acceleration is negative. This means x component of acceleration is in this direction. What is the magnitude? Magnitude is 0.05 meter per second square. And y component of acceleration is basically positive. So this is in this direction. And the magnitude is 0.30 meter per second square. So the resultant acceleration will be somewhere like this. So this is the x component of acceleration, this is the y component of acceleration, and this is your resultant acceleration. Now if you remember, in the previous classes we derived an expression how to calculate angle, this angle alpha, from the positive direction of x-axis. So we said we can calculate this angle, or sometimes this is also called beta. So you can so for velocity generally we reserve alpha term, and for acceleration we reserve beta term. So this angle is beta. So we can write tan beta is equals to A by E divided by AX. This is very simple. You can basically prove this. Now for this problem, A by E is equals to 0.30 meter per second square. And AX is negative 0.05 meter per second square. So if you calculate, you will get beta is equals to 31 degree. So in this case, if you take tan inverse of this term, so you will find beta is equals to basically minus 31 degree. Now what this minus sign says, this minus sign is saying this angle, if you count from this side, this angle is 31 degree. But if you want to count from this side, in that case, you have to basically subtract from 180. So I can say this angle is how much? So this angle is basically 180 minus 31. So this is 149 degree. So from the positive direction of x-axis, the resultant acceleration vector is making an angle of 149 degree. And what is the magnitude of that acceleration? Magnitude is 0.58 meter per second square. So in this video, we discussed about how to calculate average acceleration and instantaneous acceleration. So the takeaway message is you have been given some x coordinate and y coordinate. It is easy to work in terms of component. First find out the Vx and Vy in terms of expressions. Once you have this expression for Vx and Vy, you can calculate these velocity at any given point of time and calculate those velocity, and then average acceleration is simple, that is change in the velocity divided by total change in the time, that is time interval. So that will give you the average velocity, average basically acceleration. Now instantaneous acceleration, you have to differentiate the velocity and then plug the time period for which you want to calculate the acceleration. Remember, the acceleration is a vector quantity. You have to calculate the magnitude of acceleration as well as you have to give answer for the angle that this is making with the positive direction of the x-axis. For this problem, positive direction of x-axis, this is making an angle of around 149 degree. I hope you enjoyed this video, and if you enjoy, please share with your friends, and I will see you in the next video. Thank you. Hello friends. In the previous video, we have seen how to write acceleration in Cartesian coordinate, and that is the instantaneous acceleration. And particularly we discuss for case of two-dimensional motion. So two-dimensional motion is a motion in which objects move along a plane. This means velocity has two components. It has Vx and Vy component. And at that point of time, we have learned how to calculate acceleration of an object if it is moving in a two-dimensional plane. In terms of Cartesian coordinate, we can write acceleration something like this. So acceleration vector A is equals to x component of acceleration multiplied by the unit vector in the x direction plus y component of acceleration multiplied by the unit vector in the j direction. So this is a way by which we can represent the acceleration vector. Now in this case, the first term basically denotes the component of acceleration along the x direction, and the second term denotes component of acceleration along the y direction. So this is one way in which we can represent the acceleration by breaking the total acceleration into two components, that is x direction component and y direction component. Basically, there is another way to write the acceleration vector, and that is decomposing the total acceleration into two directions, but this time this direction are not Cartesian direction, x and y direction. This time direction is in the direction of velocity and in the direction of perpendicular to the velocity. So what we are saying? We are saying we can represent alternatively the acceleration vector parallel to velocity vector and perpendicular to the velocity vector. So let us try to understand all this. So let us say I have a particle and this particle is moving along this path. So this is the projectiles or this is a particle's path. This is not a case of projectile. It can be projectile also. So this is a path of particle. Now at certain point of time, this particle is at point P. So this is the particle position at say t is equals to t1. Now this particle will have a velocity. So if I make a tangent at point P, I will get the direction of velocity of this particle. So this line is basically tangent to point P, and that is basically direction of velocity. So velocity is directed in this direction. So this is the direction of velocity. Now we can also choose another axis, this axis. This axis is perpendicular to direction of velocity. So we have considered two axes. One axis is in the direction of velocity, that is tangent to the path. Another is perpendicular to the direction of velocity. So we have two axes. One is along the velocity, another is perpendicular to the velocity. What is my target? My target is, can I break my total acceleration vector along these two axes? So let's say at point P, the acceleration vector for this particle is something like this. So this is total acceleration vector for this particle. Now what we have to do is, we have to break this into two components. So I will basically take this component and take this component. So this component is here, the first component, that is along the perpendicular to the velocity direction, and this is parallel to the velocity direction. So this is parallel to the velocity direction. So now I have two velocity component, basically two acceleration component. One is along the velocity direction, another is perpendicular to the velocity direction, or I can say perpendicular to the path, because the direction of path and direction of velocity and direction of tangent all are in the same direction. So this component of acceleration is basically component of total acceleration parallel to the path, or I can say component of total acceleration parallel to velocity, or in the direction of the tangent. Similarly, this component of acceleration is component of acceleration perpendicular to the path. So this is perpendicular to the path. If you know this angle theta, basically you can calculate the perpendicular component and the parallel component. In that case, perpendicular component will be a cos theta. So I can say perpendicular component will be a cos theta, and the parallel component will be a sin theta. So we can calculate these two components. Now why we are basically decomposing acceleration into these two components? What is the advantage of using all this? So there is advantage, and the advantage is the parallel component of acceleration, that is parallel to the direction of velocity or tangential direction acceleration, basically gives you the change in the speed. That is important point. So this gives you change in speed, and perpendicular component, that is in this direction, gives you change in the direction. So if you are measuring the perpendicular component, you are basically measuring the change in direction, and if you are measuring the parallel component, this means you are measuring the speed change. So these two directions are useful because they give what is the magnitude of direction change, or how the direction is changing and how the speed is changing. Parallel component, a speed change; perpendicular component, direction change. To further illustrate, let us try to take some special cases. What we can do is, so this is my total acceleration vector. So this is the total acceleration vector. This is the perpendicular component, and this is the parallel component, and the particle is moving along this curved path. and particle as t is equals to t1 at point P, as I said earlier. Now what will happen if my perpendicular component is 0? In that case, I will only have parallel component of acceleration. So this component will only survive. The perpendicular component is 0 in this case. Now if you remember what I said earlier, the parallel component denotes the change in the speed of the particle. So let us try to see. At this point, at point P, velocity of this particle is v. So this is the velocity. I can show the same thing something like this. So this is the velocity. Now after certain point of time, this velocity has increased and this velocity is now v2. So this velocity has increased and this velocity is again in the same direction. This is because this component of acceleration is 0. So this means only velocity is changing, magnitude is changing, direction of velocity is not changing. So what I am saying, when the perpendicular component of acceleration is 0, this means only the direction, only the magnitude is changing, direction is not changing. This means the object is moving in a straight line. So if the object is moving in a straight line, the direction of velocity first is v1 in this direction, then v2 will also be parallel to this vector. So v1 is this vector, then v2 will also be parallel to this vector. So magnitude can increase, but the direction will remain same. So v2 has same direction as v1. Now if you calculate change in velocity, that is v2 minus v1, so this will give you change in velocity vector. Once again, the change in velocity vector is also in the straight line, and this is in the direction of v1 and this is in the direction of v2, because v1, v2, delta v all are having same direction. So this means if tangential component is only there, perpendicular acceleration component is 0, in that case I can say object is moving in a straight line, because the motion is not changing the direction. So this has only possibility when the object is moving in the straight line. In this case you can see acceleration is what? Acceleration is simply dv divided by dt, or you can write in limiting case dv by dt. So this is acceleration. So if you divide by dt, you can get the acceleration. So direction of acceleration will be same as direction of velocity. So this is direction of change in velocity. So this is the direction of final acceleration. So you see, when the speed is changing only, in that case you will have perpendicular component of acceleration is 0, only tangential component or parallel component will exist, and in that case only a speed will be changing, particle is moving in a straight line, and there is no change in the direction of the particle. And this is here. So only in this case only a speed changes, not the direction, and acceleration in this case is parallel to the velocity. So as I said, if you have perpendicular component is 0, you have only one component that exists, that is parallel component, tangential component, and the speed is changing. So this is one advantage, that if you know that object is not changing its direction, it's only changing its speed, this means you know that the perpendicular component is 0, only a parallel component of acceleration will be there. Now the second situation we can have, what will happen in the second situation? In the first case I said the perpendicular component is 0 and the object is moving in a straight line. Now in the next situation I can say the tangential component or parallel component is 0. What will happen in that case? That is, now in the second situation when the parallel component is 0. So what will happen when the parallel component is 0? So this means now this time this component is 0. So this component does not exist. So acceleration is the total acceleration in this case is like this, but the parallel component is 0. This means only this part of acceleration exists. This means Now only there is a direction change. There is no a speed change because this component of acceleration, that is tangential component of acceleration, tells you about the speed change. But there is no speed change because there is no component in this direction. So this time only acceleration will change. Only the perpendicular component of acceleration will change. Now when you have such kind of situation, velocity component is constant, that is a speed is constant, magnitude of velocity is constant, a speed is not changing, only the direction is changing. When you see such kind of situation, you see such kind of situation in circular motion. When the speed is constant but the direction is changing, each point direction is changing. So you have a circular motion case where the parallel component is 0 but the perpendicular component only exists. This means only direction change exists, there is no speed change. To illustrate, let us say I have an object and this object is moving and the velocity at certain point of time, the velocity is v1. Now since this is a case where the parallel component is 0, this means velocity is not changing. So at certain point of time, the magnitude of velocity will remain same. So at certain point of time, let's say t2, magnitude of velocity will be same. This means v1 has this much of length, then v2 after some time will also have same amount of length. So this is the velocity vector v2 at time t2. What will be the only difference? The difference is the direction. Initially your velocity is along this direction, now velocity is along this direction. So direction has changed. There is only difference. And this angle by which this direction has changed is phi. Let's say this angle is phi. So we can basically make this triangle and then we can find what is delta V. So V2 minus V1. So I can write in this triangle. So V1 plus delta V is equals to V2. So what I am using? I am using simply triangle law of addition of vector. So V2 is equals to V1 plus delta V. In other words, delta V is equals to V2 minus V1. So this is the direction of delta V. Now what is acceleration? Acceleration is nothing but dV by dt. In other words, I can say direction of acceleration is same as direction of change of velocity. This means this is the direction of dV, then in the same direction parallel to this direction will be the direction of acceleration. So this is the direction of acceleration. So that is perpendicular to the path, perpendicular to the velocity vector. Now as you take this phi very small, as phi becomes smaller and smaller, this dV basically becomes perpendicular to V1 and also perpendicular to V2 because this angle is very small. If you take delta t tends to 0, in that case this angle becomes smaller and smaller and this becomes perpendicular to this path and perpendicular to this path. This means your dV vector or acceleration vector will be perpendicular to V1 and perpendicular to V2. So your acceleration is basically perpendicular to V1 or V2 with constraint that delta t tends to 0 for a small amount of time. So this is what here I have written. For a small change of delta V, for a small change delta V is, for a small change of delta V I can say delta V is perpendicular to V1 and this is also perpendicular to V2. In this case only direction changes, not the speed. So as I said, if your tangential component, parallel component of acceleration is 0, in that case there is no speed change, only change in direction of velocity. So there is no change in the speed. As phi goes to 0, delta V is perpendicular to velocity vector V1 and velocity vector V2. So this is obvious. So as this angle goes to 0, this vector, that is the acceleration vector, and which is same or parallel to the delta V vector, both becomes parallel to perpendicular to V1 and V2. That is 90-degree angle between V1 and delta V and V2 and delta V. So this time you see if you have tangential component is 0, you have acceleration perpendicular to the velocity. So your total acceleration is perpendicular to velocity, because in that case what is happening? Parallel component is 0, tangential component is 0, only perpendicular component exists, and in that case I can say velocity vector and total acceleration vector is perpendicular to each other. And finally, what will happen if both components exist? This means you have the tangential component and you also have the parallel component. So you have the tangential component of acceleration that exists, that is parallel component of acceleration, and perpendicular of component of acceleration. In the previous two cases, what we did? We did, in one case this component does not exist, in another case we said this component does not exist. But now what I am saying? Now I am saying, now both components are there. So this component is non-zero and this component is also non-zero. This means your total acceleration vector will be something like this. So this time your magnitude of vector, that is speed, is changing, and that is given by this term, and direction is also changing, that will be given by this term. So if you have an object that is moving in the straight line, in that case you have situation like this situation. And if you have an object that is moving in circle, in that case you have this situation. So in circle you have this situation. Now you have a situation in which these two components exist. This means it's neither in a straight line, not in a circle. It's some trajectory. It's not a straight line. It's some curved, but not circle. So in that case, you will have this situation, that acceleration will exist. So total acceleration will have both component. This will have tangential component and this will have perpendicular component. Now for this general case, there are three possibilities. We will discuss different possibility. So different situations for a particle moving along a curved path. So if a particle is moving along a curved path, different situation can arise. What are these different situations? First situation, when the speed is constant along a curved path. As I said earlier, a speed is constant. This means what? The tangential component, the parallel component is 0. A speed is constant. This means the perpendicular component will only be there and tangential component is 0. So this means in this special case, this component is 0. So there is no acceleration parallel to the velocity vector. We have only acceleration that is perpendicular to the velocity vector. So I can say in this case, acceleration will be inclined, or will be total acceleration will be in this direction, that is perpendicular to the direction of velocity. So when a speed is constant along a curved path, I can say acceleration is normal to the path. So this is total acceleration and this is the path direction or tangential direction or direction of velocity. So total acceleration is perpendicular or normal to the path or to the velocity vector. Second situation can arise when a speed is increasing along the curved path. So this means the speed is increasing. So this means you will have tangential component, you will have parallel component. So this is your parallel component. And in this case, you will also have a speed is increasing along a curved path. So this means you will also have this component. So you will have both component of acceleration. You will have this component of acceleration and you will also have this component of acceleration. And if you take sum of these two, you will get the resultant. So resultant will be in this direction. So your resultant will come in this direction. The same thing is shown here. I can show this like this. So you will have something like this. So this is your parallel component of acceleration and this is your perpendicular component of acceleration, and if you sum, this is your total acceleration. So this is your total acceleration. So in this case you can see acceleration is ahead of this normal vector. So this is your normal vector. So this is your normal and then your total acceleration is somewhere here. So you can say acceleration points ahead of the normal. So when a speed is increasing along the curved path, the total acceleration is ahead of the normal vector, or normal I can say. So A points ahead of the normal to the path, or normal to the velocity vector. And third situation, you can answer yourself. What will happen when the speed is decreasing along the curved path? So you have to answer yourself. What will happen if a speed is decreasing? In the previous case, the speed was increasing. Now the speed is decreasing. What will happen? So speed is decreasing. This means you will have a tangential acceleration, but that tangential acceleration will be in this direction. And you will have a normal acceleration because direction is also changing. So you will have a normal acceleration, and that will point in this direction. So this is the normal acceleration, and this is the tangential acceleration. Why the tangential acceleration is in the opposite direction? Because there is a decrease in the speed. So increase in the speed this side, decrease in the speed this side, because the direction of a speed is in this direction. So now if I take the resultant of this vector, that is the perpendicular component, and this is parallel component, and if I take resultant of this 2, I will get this vector, that is acceleration vector. Now see, this acceleration is behind the normal. So normal is here and this acceleration is here. So in this case I can say acceleration points behind the normal. So if your speed is decreasing with time, acceleration vector is behind the normal vector, or normal perpendicular to the velocity, that is the normal to the velocity, or normal to the path. So I can say A points behind the normal to the path. So we illustrated how you can basically use the idea of tangential component of acceleration and normal component of acceleration to analyze motion on a curved path. In summary, I can say if you have only tangential component, this means object is moving in a straight line. If you only have perpendicular component, object is moving in a circle. And when you have both component, object is moving on a curved path, increasing the speed, and this also has change in direction of the acceleration. Now we will illustrate this using an example. So this example says, so we have a particle, and this particle has two acceleration component. Initially the total acceleration is given. This is the total acceleration of this particle, and this is the direction of velocity. So I know the direction of velocity of this object. So this object is at certain point of time, this object is moving in this direction. We have to calculate the component of acceleration along the direction of velocity and perpendicular to the direction of velocity, and the acceleration is given. This is 1 meter per second square. So magnitude of acceleration is given, that is 1 meter per second square, and I have to calculate what is the parallel component and what is the perpendicular component. So this is your acceleration, and this is your parallel component, and this is your perpendicular component, and this angle is theta. So if this angle is theta, so I can use this right angle triangle and I can calculate this one. So this angle is theta, and that theta is 30 degree in this case. So I can write cos theta is equals to A parallel divided by A, and I am writing in terms of magnitude. So A parallel is nothing but A cos theta. A is given, that is 1 meter per second square, and this cos theta is cos 30 degree, and cos 30 degree is nothing but root 3 by 2. So this is root 3 by 2 meter per second square. So this is A parallel acceleration. Similarly, I can write A perpendicular, this will be A sin theta, and theta is equals to 30 degrees. So I can write 1 meter per second square times sin 30 is nothing but 1 by 2. So I will have 1 by 2 meter per second square is the acceleration in this case. So we calculated perpendicular component, and this is the parallel component. So in this video we learned how to use a different set of decomposition of acceleration. Generally we use Cartesian coordinate, but when you have an object that is moving on a curved path, we try to use parallel to the velocity and perpendicular to the velocity. So we decompose the acceleration parallel to the velocity and perpendicular to the velocity, and then we analyze the motion. This is particularly important when we will go to the circular motion chapter. In that case, velocity magnitude is constant, speed is constant, speed is not changing, only the direction is changing. This means perpendicular component of acceleration is only changing, the normal to the path is only changing, there is no change in the tangential acceleration. So we'll come to this again in the circular motion chapter. For the time being, thank you, and I hope you have enjoyed this video and you will share with your friends. See you in the next video. Bye. Hello friends. In the last video we have seen how to decompose acceleration of an object when this is moving on a curved path. Basically there was two approaches. In the first approach, what you can do is you can decompose the total acceleration in Cartesian coordinate system, that is one along the x-axis and other along the y-axis. That is a typical approach for decomposing the acceleration. But when you have an object that is moving on a curved path, it is a good idea to decompose the acceleration vector in radial and tangential direction. What that mean? That means like you have to decompose the acceleration in direction of velocity or in a parallel direction to velocity and perpendicular direction to the velocity. For example, let's say if I have an object and this object is moving on this path. So this is path on which object is moving, and certain point of time this object is here. So this is object P and this is moving, so I can basically know what is the direction of velocity. Direction of velocity is tangent to the path. So this is the direction of velocity. Now this object will have some acceleration. Now let's say acceleration is in this direction. So this is the total acceleration of this object. Now this is the direction of velocity, and we can think of another axis that is perpendicular to this velocity vector. So this is a axis that is perpendicular to this velocity vector. So one axis is along the velocity, another axis that is perpendicular to the velocity vector. Now what I am saying, now I can decompose this acceleration. So this is my acceleration vector, and I can decompose this acceleration one along the velocity and other perpendicular to the velocity. So now this is parallel to velocity and this is acceleration component perpendicular to the velocity. So we have basically decomposed acceleration into two components, parallel components and perpendicular component. What actually they signify? Basically parallel components tells you about the change in a speed. So this tells you about change in a speed. Similarly, perpendicular components, this tells you about change in direction. For example, if we have an object and this object is moving in a straight line, in this case I can say there is no change in the direction. This means perpendicular component of acceleration is 0 in this case. So if an object is moving in a straight line, I can say perpendicular component is equals to 0. Similarly, if an object is moving in a circle, for example, this is the circle in which the object is moving, what happens in this case? The speed does not changes, the magnitude of velocity does not changes, but the direction changes. At this point, this is the direction of velocity, at this point, this is the direction of velocity. So the direction of velocity changes. So I can say in this case, the parallel component of acceleration is equals to 0, because there is no change in the speed, but perpendicular will not be 0, because in that case there is a change in the direction. Now we will illustrate all this using a problem. So this problem says a skier moves along a sky jump ramp as shown in the figure. The ramp is straight from point A to point C and curved from point C onwards. So this is the skier and she tried to make a sky jump on this ramp that is something like this. So this ramp has two portions, one is curved portion, another is a straight portion. So question says point A to point C, this is the straight portion. The skier speeds up as she moves downhill from point A to point E. So as she is going from point A to point E, there is an increase in the speed. So she speeds up, where her speed is maximum, and point E, this point is maximum speed. So at point E I can say here she has maximum speed. So speed is maximum at this point. She slows down. So she slows down after passing the point E. After passing point E, her speed decreases. Draw the direction of acceleration vector at each of the points, that is B, D, E, F. So what is given in this problem? So we have been given from A to C, that is a straight path. So this is a straight, that is one thing. And C to F, that is basically curved path. And it is also given maximum speed is at E, and when he is going or she is going from A to C, there is an increase in speed, and not only A to C, up to E, basically there is an increase in speed. And then after this there is a decrease in the speed. We have to show the acceleration vector at different points. So let us first consider at point B. So what will be the direction of acceleration vector at point B? So at point B, so portion A to C, that is this portion, is a portion of a straight line. There is no change in the direction. So as I said, if there is no change in the direction of velocity, perpendicular component is equals to 0. So what we will have? We will have only parallel component of acceleration will exist. This means at point B, the acceleration vector will be in the direction of velocity. That is, I can say at this point acceleration is in this direction. So acceleration is same direction. Acceleration is in the same direction as the velocity, because perpendicular component is 0. There is no perpendicular component. Now let us consider point D, E, F. So at point D, E and F. So now first consider point D. So at point D there is an increase in speed. So we will have a speed is increasing. So we will have parallel component. What about perpendicular component? This will not be 0 because there is a curved path and the direction of velocity is also changing. So at point D, you have some component of acceleration that is parallel, and you also have some component of acceleration that is perpendicular. So this is basically also direction of normal. So this is the normal direction. So if you take the resultant of these two, you will have something like this. So this is the total vector at point D. So you see, at point D I can say acceleration is ahead of the normal. So this is my normal and acceleration is somewhere here. So I can say acceleration in this case is ahead of the normal. So A vector is ahead of normal. So this is what I can say for point D. So this is for point D. What about point E? At point E, a speed is maximum. So there is no change in the speed. So if there is no change in the speed, I can say the parallel component of acceleration is equals to 0. but perpendicular component of acceleration will still be there. So what will be the direction? Once again, this is the normal direction. So in this case, I will have acceleration that is along this direction. Because parallel component is 0, so we will only have one component, that is perpendicular component, and that will be along the normal. So this is acceleration vector at point E. So I can say in this case A is, the acceleration vector is along the normal. So this is along the normal. What about point F? So let us find acceleration at point F. Now at point F, there is a decrease in speed. So speed is decreasing. So we will have parallel component because the speed is decreasing. So we will have parallel component. So parallel component will be there. What about perpendicular component? Perpendicular component will also be there because direction at F is changing because this is a curved path. So direction is also changing. So we will have perpendicular component as well as parallel component. So this is similar to situation D. Only difference we have, at point D there is a speed up. At point F there is a speed decreasing. So slowing down. So what will happen in this case? So this has a, so this is the direction of normal. So this has a perpendicular component, but this is slowing down. So acceleration will be in the backward direction. So if you take resultant of these two, it will come something in this direction. So this is the resultant acceleration at point F. So now I can say at point F, basically acceleration is behind the normal. So this is my normal at this point, and this is acceleration vector. So I can say acceleration is behind the normal. So acceleration is behind the normal vector. So in this video we learned how to show the direction of acceleration of an object when this object is moving on a curved path. Basically there are two components, parallel component and perpendicular component. Parallel component tells about the change in the speed and perpendicular component tells about change in the direction. Now we have seen if I have object in a straight line, in that case the perpendicular component will be 0, that is point B. Point D, E and F, these are moving on a curved path, so we will have normal as well as tangential component of acceleration. At point E, that is a special case. In that case a speed is not changing, and that's why the parallel component is 0. In some cases, for example in point D, the acceleration vector is ahead of the normal, and at point F the acceleration vector is behind the normal. I hope you enjoyed this video, and if you enjoyed, please share with your friends, and I will see you in the next video. Thank you. Hello friends. In this video we will learn about projectile motion. Projectile motion is an example of motion in two dimensions, and in this case motion generally happens in vertical plane. So the question is, what is projectile? So when you throw an object, this can be a ball with some initial velocity, and this ball moves under the gravity, then this is called a projectile. So projectile is an object that moves under the gravity with some initial velocity, and that is projectile. And the path that it follows, the path followed by the object, is called trajectory. So two terms here we have. One is projectile, another is trajectory. So a projectile is any object that is given an initial velocity and then follows a path determined entirely by the effect of gravitational acceleration and air resistance. So if you give some initial velocity to some object and it basically moves under the gravity, and there is one more force that is acting on the object, that is air resistance, then this object is called a projectile. So what are the examples of projectile? For example, you can throw a ball, you can throw a football, you can drop a packet from a roof, or you can drop a packet from airplane, or you can shoot a bullet from the rifle. So these all are example of projectile. And the path followed by projectile is called trajectory. So if you throw a ball, it follows some path and finally it comes to the ground. Then this path is called trajectory. Now the projectile you are throwing, it can be in any direction. You can throw a projectile in the horizontal direction, you can throw the projectile in the vertical direction, or you can throw the projectile at some inclined angle from the horizontal. So these all are example of projectile. So when I am saying projectile, direction can be anything, only is you must have some initial velocity and it should basically move under the gravitational acceleration, that is g, and it should have some air resistance. In this video we will assume that there is no air resistance to make the model simple. So now let us try to derive theory for projectile motion. So whenever we have some theory, some model we derive or we develop, we make some assumption, and that assumption often called idealization. So why we need idealization? To make things simpler, to make calculations simpler. We try to understand the physical situation that is happening in actual with some mathematics. But the mathematics cannot directly translate the actual situation, and that's why we need some idealization. We need some assumption. So to make things simpler for a projectile motion, we will make some idealization. We will make some assumption. What are these assumptions? The first assumption is projectile as a particle. So we will assume that the ball or football or rifle bullet that you are throwing is a point mass. This makes easy to write equation of motion, because whatever we derived in the one dimension, we derived for a particle. So now if I assume this is a particle, I can write equation of kinematics. So that is one advantage. The second idealization is acceleration due to gravity is constant in both magnitude and direction. So we are assuming the acceleration due to gravity, that is g value, it's constant both in terms of magnitude. So magnitude we will assume some value, for example I can assume 9.8 meter per second square, and the direction is also constant, so this is acting in the vertical downward direction. So we are assuming that magnitude and direction is constant. However, the magnitude is not constant. If you go above the earth, as you go more height, as you go at more height, you will see that the g value decreases. So this kind of assumption is only valid if you are close to the earth's surface, and then you are doing all this calculation. And generally this is true, because all the projectiles and missiles and all this are long range, and this does not go to very high, and that's why we can apply this theory. So this is a logical assumption. And the second idealization is basically third, neglect the effect of air resistance. So as you know, any kind of fluid apply a resistance force. So it can be air or it can be a fluid water. So all applies resistance. So in this chapter or in this video, we will assume that there is no air resistance. So we are assuming that air resistance are absent, and that's why we can ignore the force that is coming due to the air resistance, and we can apply simple equations. And finally, we are making another assumption, that is curvature and rotation of earth is absent. So we are neglecting the curvature of and rotation of the earth. Basically, earth is not flat. Earth has a shape, rounded shape. So when you are describing projectile motion, you are assuming that earth is a flat, and this assumption is valid if your range of the projectile is not very large. You are throwing a projectile 500 meters, 600 meters, 200 meters, 100 meters. In that case, you can assume that the earth is flat. But if you are throwing a missile that is a long distance, in that case you have to basically consider the rotation of Earth as well as curvature of Earth, because Earth becomes rounded and you have to account for the rounded shape of the Earth. If the smaller range projectile you can ignore, because for a small range you can assume that the Earth is flat. So the curvature of the Earth has to be considered in the flights of long range missiles, and air resistance is of crucial importance to a skydivers. So you see, in some cases we have to account for the air resistance and we have to also account for the curvature of Earth. For example, if you have a long range missile, you have to account for the curvature of Earth. And if there is a skydiver, in that case you have to basically account for the air resistance, because he is basically flowing or diving in the air only based upon the air resistance that is coming from the down. So he is trying to minimize the effect of gravity by the opposing effect that is coming from the air resistance. In such cases, we have to analyze the motion by accounting these factors. So this figure shows a typical projectile motion. So you have a ball and this is thrown here with some initial velocity, and this is your x-axis and this is your y-axis. So object is moving in a plane that is contained by xy plane. So this is your trajectory of object, and this is in the vertical plane. So we have one plane, that is xy plane, that is fixed. So this object is not laterally moving. It's not going away from the xy plane, either in this case inside, or it is not going outside of this plane. So this is contained in this plane. So what are the important thing in this case? One important point, that is acceleration in the x direction and acceleration in the y direction. So we have given some velocity, some initial velocity to this object. Now this object is moving. So what are the acceleration? In the y direction we have one acceleration, and that is basically gravity. Now if I consider y direction is the upward direction, then this gravity is in the downward direction. So this will be minus g. So in the y direction I have acceleration that is equals to minus g. Now what is the acceleration in the x direction? So in this case, there is no acceleration in the x direction. So we can assume that ax is equals to 0. So why this is in the vertical plane? Why this does not deflect? Because there is no velocity in this direction. Sideway deflection is not possible, and gravity cannot deflect in the sideway. So why vertical plane? Why only one plane, xy plane? The reason is gravity cannot deflect sideways, and there is no sideway velocity. So gravity cannot deflect, so that's why the motion is restrained or contained in one vertical plane, and in this case this vertical plane is xy plane. Only two accelerations are present, ax and ay. In this case ax is equals to 0 because there is no force that is acting in the horizontal direction. We have assumed that air resistance or air force is 0. So that's why ax is equals to 0. Ay is equals to minus of gravity, because we will assume that the positive direction of y-axis is in the vertical direction. Now how we analyze such kind of motion? So we have a projectile, we know trajectory. The question is how we analyze such kind of motion. So analyzing a projectile motion is not a difficult task. Basically, we have learned all this. So this is just a superposition. So in this case, you see, this is a two-dimensional motion in xy plane. And now we learned in earlier videos that how we can analyze one-dimensional motion. That is, if motion is happening in a straight line. So the key idea to analyze a projectile motion is superposition. So what we will do is, we will analyze an x-axis motion and y-axis motion separately. So we will first try to analyze x-axis motion, and then we will try to analyze y motion by y-axis motion, and these two will basically superimpose, and then I can get the total motion of this particle. For example, let's say if this object is thrown with velocity u, so u is the velocity by which this object is thrown, and at alpha angle this object has been thrown. Now what is my target? My target is to analyze this motion along the x-axis and analyze this motion along the y-axis. So if I want to analyze this motion along the x-axis, what are the things that I need? I need what is the initial velocity along the x-axis, what is the acceleration along the x-axis. Then I can use all the formula that we derived for one-dimensional motion. So in one-dimensional motion we derive three formula. V square minus u square is equals to 2as. S is equals to ut plus half at square. And another formula V is equals to u plus at. So these three formula that we discussed in one-dimensional motion, and that three formula I can apply for x motion and I can apply for y motion. So if I want to apply for x direction, what is the initial velocity in this case in the x direction? I have to take component of u. So this is u vector, and then this vector will be u cos alpha, and this vector will be u sin alpha. So this velocity can be decomposed with u sin alpha and u cos alpha. So initial velocity in this case in the x direction is simply u cos alpha. What is acceleration in the x direction? In this case there is no acceleration. Now if I want to analyze bi-direction motion, what is the initial velocity in the bi-direction? That is u sin alpha. What is acceleration in the bi-direction? Now I have assumed that bi-direction is upward direction and gravity is acting in the downward direction. So in this case acceleration will be minus g. So now I know u and a, that is initial velocity and acceleration in the x direction and in the y direction. Now I can apply formula, the three kinematical equations that we derived in the previous videos. So I can use those three formula for x direction motion and y direction motion, and then I can superimpose and then I can get all the results, and this we'll see in this video. So projectile motion as a combination of horizontal motion with constant velocity and vertical motion with constant acceleration. So basically projectile motion is a combination of constant velocity in the x direction. So x direction you have a constant velocity because you have initial velocity is u. So at any time what will the v? V is equals to u plus at, and acceleration is 0. So v is equals to simply u, and u in this case is u cos alpha. So now you understand, in the x direction we have a constant velocity, that is u cos alpha, and in the y direction we have constant acceleration, that is minus g. So the projectile motion is nothing. I have to use the two facts, that is in the horizontal direction we have constant velocity and on the vertical direction we have constant acceleration. So if you use these two facts, you can analyze a projectile motion. Now here I will illustrate the bi-motion of projectile is identical. Either you throw horizontally or you simply drop the ball. So let us try to see these two cases. In one case, that is this case, we have dropped a ball with rest, and this ball is simply freely falling under the gravity. Now in this case, the yellow ball, we have thrown this ball with some initial horizontal speed. There is no vertical velocity. So you see, in both cases the vertical speed is 0. So either this case number 1 or this case number 2. So there are two balls. One ball we have thrown In the horizontal direction, one ball we have simply dropped in the vertical direction, and in both cases vertical velocity is 0 because this ball has been thrown horizontally. So vertical velocity is 0. So if you consider the vertical motion, in the vertical motion both balls are same. If you want to calculate y distance in vertical direction, what I will use? I will use s is equals to ut plus half at square. In this case, y is equals to ut plus half at square, and y is equals to initial velocity for both ball is 0, and gravity is acting in the downward direction. That's why I'm writing minus z, and this is t square. So for both ball, distance cover, that is y distance from the top, let us say this point from where the ball has been thrown is origin, 0, 0 coordinate. So in the vertical direction, both balls are basically traveling or covering the same distance in same amount of time. So this means if this ball has reached here, then this yellow ball also has reached here. This ball has reached here, then yellow ball has also reached here. So this means both balls are basically covering equal amount of distance at given point of time. So even though in this case x motion is different, one ball has fallen at this position, one ball has fallen at this position, but the y motion is identical. Both balls are traveling equal amount of distance in equal amount of time. So as I'm saying, in this case, since there is no y velocity for the second ball and the first ball, both balls are simply falling under the gravity, and both will follow same equation, and we can calculate y distance for both the ball. So we can see for this situation, one ball is dropped from rest and other is projected horizontally, but both projectiles fall the same distance in same time because both are freely falling under the gravity. Now we will try to derive expression for distance x and at any point of time what is y coordinate of a projectile when it is thrown with some angle and with some velocity. So let's say I have, this is my x-axis and this is my y-axis, and this is the projectile that has been thrown at angle alpha and with initial velocity u. Now this will follow a projectile. It will be something like this. Now my target is to find at any given point of time what is its x coordinate and what is its y coordinate. So this is the projectile at certain point of time. So I want to find what is the position vector of this projectile at certain point of time t. So position vector means I want to know what is x coordinate, what is y coordinate. And as I said, now we can basically decompose this motion into two directions. First, I will decompose in the x direction. And in the x direction, what is the velocity? So velocity in the x direction we will have, that is the initial velocity is u cos alpha. So this is u cos alpha. And what is the acceleration in the x direction? So this denotes x direction. What is the acceleration in the x direction? Acceleration is 0. Similarly, y direction I can write what is the initial velocity in the y direction. So in the y direction, we have a velocity and that is u sine alpha. And this is upward direction, that's why this is positive. What is the acceleration in the y direction? This is minus of gravity because this is acting in the downward direction. Now I have to find the position vector. And if you remember, in previous one-dimensional motion we derived our formula, that is s is equals to ut plus half gt square. Now I will use this formula for x motion and for y motion. So if I apply along the x-axis, I can write x distance is equals to ut, and a speed in the x direction is u cos alpha and time is t, and there is no acceleration in this case. Basically we write ut plus half at square. So there is no acceleration in the x direction. So what I'm doing, I'm simply applying this equation in the x direction, and then distance in the x direction is x, velocity, the initial velocity in the x direction is u cos alpha, and acceleration in the x direction is 0. So we have applied this equation in the x direction. So from here I can write, so this is same equation. So let's remove this because next I will use the same equation for y direction. So now I can write x is equals to u cos alpha times t. So this is my x value. Now similarly I can calculate y coordinate. So if I write equation of motion in the y direction, I can write y is equals to, what is the speed in the y direction, initial speed, that is u sine alpha. So if you remember, we have just written the initial speed is u sine alpha into t plus half into acceleration. What is the acceleration in the y direction? That is acting in the downward direction. That's why this is minus g, and this is t square. So this is the equation of motion for y direction, and I can write y is equals to simply u sine alpha t minus half z t square. So this is my y coordinate. Now once I know my x and y coordinate, basically I can write position vector. So what is position vector? X I cap by j cap. So this we discussed in the previous classes also, that position vector can be written as xi plus yj, and in this case now I know my x. What is x? Simply u cos alpha times t, and this I, so this becomes I cap. So x component plus y component. What is y component? U sine alpha t minus half zt square, and then this j cap. So this is my position vector. So x component of position vector is this, and this is the y component of the position vector. So once I know the position vector, I can basically calculate magnitude of distance from the origin. For example, now I know my xy. So this position coordinate xy I know. So we can basically calculate what is the distance of this point from the origin. So this is my position vector. So this is r. And if I take magnitude of this, I can basically calculate what is the distance from the origin. So this is origin in this case. From the origin, what is the distance of the point at point P, that is basically at any point of time t, what is the position of this object, of the position of this projectile. So if I take magnitude of r, I can calculate distance of projectile from the origin, and the magnitude of r is nothing but under root x square plus y square. This you can basically prove. For example, if you want to calculate this distance, and this distance is x, this distance is y, then you can use Pythagoras theorem, and then this distance, that is magnitude of r, will be simply under root x square plus y square. So now I can write r is equals to, so this is a square root of x is u cos alpha t whole square plus y is what? U sine alpha t minus half zt square, and then you have to square this term and then sum and then take root. So this is the distance from the origin. So we calculated the position vector and distance from the origin at any given point of time. Now we can also calculate velocity of projectile at any point of time. Basically, if you see, if you have this projectile, So this is your projectile. So at any given point of time, this has two components of velocity. One is x component, another is y component. So this is your vx and this is your vy. And initially it has been thrown with velocity u. So once again, we will use the same idea. If you remember, in the one-dimensional motion, we have a formula v is equals to u plus at. So I will use the same formula, but now I will use in x direction and the y direction. So if you remember, x direction acceleration is 0 and initial velocity in the x direction is simply u cos alpha. In the y direction, acceleration is minus z and the velocity in the y direction is simply u sine alpha. Now I have these two things and I have this kinematical equation, that is v is equals to u plus at. Now I can apply this formula in the x direction first, that is I will take x component of velocity, initial velocity and acceleration. So let us apply this in the x direction. So I can write Vx is equals to Ux. Ux is simply u cos alpha plus acceleration in the x direction is 0. So this is simply u cos alpha and this is t, u cos alpha. V is equals to u plus at. So sorry, so this is not t here. So simply u cos alpha. So Vx is equals to u cos alpha. You see, very important point. Velocity in the x direction is constant, u cos alpha. So this does not depend upon time. So either the projectile is here or projectile is here or projectile is here. In all cases, the velocity in the x direction is simply u cos alpha. Now what about y direction? I can calculate velocity in the y direction. I can use this formula v is equals to u plus at. So vy is equals to u and the y direction velocity is u sine alpha plus at and acceleration in this case is minus z times t. So this becomes u sine alpha minus gt. So you see, the velocity in the y direction decreases. And you can find at what time the velocity will be 0. So basically you can find when you will have time is equals to, so when this becomes 0, so u sine alpha minus gt is equals to 0. This gives you t is equals to u sine alpha by g. So velocity in the y direction is not constant. So first observation is velocity in the y direction decreases because u sine alpha minus gt. So something has been subtracted. So velocity in the y direction is maximum here, t equals to 0, and then it decreases. So some point of time this velocity will be less, and at top point this velocity will be 0. Now, what will happen if t is greater than u sine alpha by z? In that case, velocity starts getting negative. So, after this top point, the velocity will start decreasing and it will be basically negative. So, this will be negative, and finally, when this lands on the ground, this will have same velocity that was initially, but in the different direction, that is in the opposite direction. Just to illustrate this bidirectional speed, so let us consider this is the projectile. Now the y velocity is maximum at 0, that is u sine alpha. Now y velocity is decreasing. Here we'll have a smaller, here we'll have a smaller, even a smaller, and here you will have 0 velocity. And then it's getting negative. So increasing in the downward direction, and maximum value will have when this projectile basically hits the ground. At that point of time we will have again, this is u sine alpha. And this you can prove by many ways. One way to prove this is energy conservation. Since the energy of this projectile is conserved, we can say the initial velocity in the vertical direction and initial velocity in the horizontal direction is conserved, and finally you will have same velocity in the vertical direction and the horizontal direction when this projectile landed. So at this point of time, x velocity is always constant, that is u cos alpha. So this is u cos alpha. This is always constant. This is always u cos alpha. So x velocity at any point of time in the motion of projectile is always u cos alpha. Only the y vertical velocity is changing. The y velocity is changing. So this basically decreases fast, comes to 0 at certain point of time, then it becomes negative, and finally the magnitude is same as the initial velocity at the point of landing, but the direction is opposite. So now I know my x component of velocity and y component of velocity. I can write velocity vector. So what is velocity vector? Velocity vector is equals to vx I component plus vy z component. And what is x velocity? This is simply u cos alpha, and then I have to multiply I cap. What is y velocity? This is u sine alpha minus gt. So this is u sine alpha minus gt, and then this is j cap. So this is the y velocity at any given point of time. So once I know velocity, I can basically calculate the speed, that is magnitude of velocity. So magnitude of a velocity is simply x square and velocity x square plus velocity y square, and then take the root of this. Then you can get the magnitude of this velocity. So this will be simply, you have to plug in this case u cos alpha whole square plus u sine alpha minus gt, and then this whole square, and then take the root. This is your magnitude of the velocity at any given point of time. You can also calculate what is the angle alpha. So this is your projectile, and certain point of time this is your x velocity, and this is your y component of velocity, and this is your basically velocity, total velocity at any given point of time. Then you can calculate this angle alpha certain point of time. So this will be what? This will be simply Vy. So this is Vy divided by Vx. So you can write Vy by Vx, and this will give you the tan alpha. So in this case I can write tan alpha is equals to Vy, that is u sine alpha minus gt divided by Vx, that is simply u cos alpha. So this is u cos alpha. So in this video we have learned how to analyze projectile motion, and we said projectile motion is nothing but superposition of two-dimensional, 1D motion. So if you have 1D motion, you know how to analyze 1D motion, and then you analyze 1D motion in two different directions, and that is your projectile motion. One important point is you should know what is the initial speed in the horizontal and vertical direction, what is the acceleration in the horizontal and vertical direction, and then you can use three kinematical equations. Once you know how to use kinematical equation, you can calculate position vector of projectile at given point of time, and you can calculate velocity vector of a projectile at any given point of time. And you can also calculate angle, the magnitude of a speed, and you can also calculate magnitude of position vector, and you can also calculate angle between vertical speed and horizontal speed. In other words, what is the angle that the projectile is making from the horizontal plane. So I hope you enjoyed this video, and if you like this video, then please share with your friends, and I will see you in the next video. Thank you. Hello friends. In the last video we said, if you have a projectile motion and you want to analyze the projectile motion, you have to consider motion in two different directions. So to analyze the projectile motion, you have to write equation of motion along x-axis and equation of motion along the y-axis, and then this becomes very easy to analyze projectile motion. Now in this video, we'll see how we can derive expression for trajectory. So what is trajectory? Trajectory is the path in which projectile moves under the gravitational field. So we want to find equation of motion for this path. This is basically trajectory. Sometime in mathematics this is also called find the locus, in which direction this point is moving. So what are the points for which this object is moving? So let's say I have a projectile, and this projectile is thrown with velocity u, initial velocity u, at angle alpha, and I want to find equation for this curve. That is, I want a function in terms of x and y, where x is the coordinate of the projectile at any given point of time and y is the coordinate of projectile at any given point of time t. So basically in equation of trajectory we will not have time, we will simply have x and y. So how will you derive this equation? The idea is again same. First you have to write initial velocity in the x direction. So what is the initial velocity in the x direction? So this is the velocity u. So if you take component of u, then in this direction I will have u cos alpha. So this is simply u cos alpha. What is the velocity in the y direction? Initial velocity. So this will be u sin alpha. So velocity in the y direction, the initial velocity is u sin alpha. What is the acceleration in the x direction? Since there is no force acting in the x direction, acceleration in the x direction is 0. What is the acceleration in the y direction? Now since I have assumed my y-axis is positive in the upward direction and gravity is acting in the downward direction, so my gravity is basically negative acceleration. So I have to use a by e is equals to minus g. So now once I have this, I can basically find equation of trajectory. And if you remember, if a object is moving in one dimension, at that point of time we derived a formula, and that formula is you can calculate distance using this formula. S is equals to ut plus half at square. So in this expression, s is the distance, u is the initial velocity, a is the acceleration, and t is the time. So now what I will do is I will use this expression in the x direction and in the y direction. So if I use this equation in x direction, so let us find equation of trajectory. First I will use this expression for x direction. So what is the distance in the x direction? So what I will do is I will put a subscript sx ux t plus half ax t square. So what is the distance in the x direction? Let's call this distance is x. What is the initial speed in the x direction? U cos alpha. And this is time. What is the acceleration in the x direction? This acceleration is 0. So x is equals to simply u cos alpha times t. So this is my first equation. Now I can again apply the same formula for y direction. So if I apply the same formula for y direction, I can write y is equals to, now this will be, okay, let me write something like this. So this will be s by is equals to u by t plus half a by t square. So what is sy? This is distance in the y direction, simply by. uy is nothing but u sine alpha and this times t. What is acceleration in the y direction? So this is minus z and this is equals to t square. So I have u sine alpha t minus half zt square. So now I know x coordinate and y coordinate of this projectile at any given point of time. Now what we have to find the trajectory equation. So equation will be in terms of x and y. It will not include time. For the time being, we have time in the expression of x. We have time in the expression of y. So we have to remove time. We have to basically consider time elimination. So what we can do is we can calculate time from equation 1. So from equation 1 I can write what is time. So this is equals to x divided by u cos alpha. And now once I have this time, I can plug into second equation. So if I plug into the second equation, I will have u sine alpha t is equals to x divided by u cos alpha and then minus, so this is this term, minus half z, and time is x by u cos alpha and this is whole square. So now I can write y is equals to u cancel, so I will have x tan alpha minus half and this is gx square and this divided by u square cos square alpha. So I can also write y is equals to tan alpha, this is a constant, times x minus this is z divided by 2u square cos square alpha, this is another constant, and this is multiplied by x square. So this is the equation of trajectory. So this is the equation of trajectory, and this term does not include time in the final expression. It only includes x by alpha and initial velocity u. So this is the equation of trajectory. And if you remember in mathematics, if you have a function like this, we call this as a parabola. So I can write tan alpha is a constant, so I can write y is equals to b is a constant, and c is basically this term g divided by 2u square cos square alpha, that is another constant, and this multiplied by x square. So this is equation of parabola, something like this, y is equals to bx minus cx square. So this is the equation of parabola. So trajectory in this case is parabola. So if you throw a projectile, it is going to follow a parabolic path. The trajectory will be a parabola. In practice also you see many examples of such parabola. For example, the trajectory of bouncing ball. So the trajectory of bouncing ball is basically a parabola. For example, in this case, if you throw a ball, this goes like this, then this goes like this, and then this goes like this, and this continue, and finally it comes to rest. So these are the trajectories. So this is one trajectory for one period of time. This is second trajectory. So second parabola, third parabola, fourth parabola. So these are all successive parabola. So you can see if you drop a ball with some angle. So let's say you are dropping a ball with some angle and you also have some velocity. The path or the trajectory is a parabola. Another example is volcano. So trajectory of molten rock ejected from volcano. So if you have, in this case, these are the molten rocks that is coming. So this is, some is going like this, some is going like this, some is going like this, some is going like this. So they all are basically following parabolic path. Trajectories are nearly parabolic. So there are many situations in which you see parabola or you see projectile that follow parabolic trajectory. So in this video we have seen how we can basically derive equation of trajectory of a parabolic path. The key idea is you have to write equation of motion along the x direction and equation of motion along the y direction, and you have to use kinematical equation S is equals to ut plus half at square, where S is the distance, u is the initial velocity, a is the acceleration and t is the time. Once you have written these two equations, your equation contains a unknown variable time, so you have to eliminate the time from these two equations and then you will get the trajectory equation. And the equation of trajectory in this case is a parabola, and we see in also many situations that follow parabolic trajectory in the daily life. For example, if you throw a ball on a surface with some inclination, it follows a projectile or it follows a parabolic trajectory. Volcano also shows parabolic trajectory. So I hope you enjoyed this video, and if you enjoy, please share with your friends, and I will see you in the next video. For the timing, thanks and bye. Hello friends. In the last video we discussed about concept of projectile motion, and we said if you have a projectile motion you can solve the problem related to projectile motion very easily. One important point you have to consider is you have to decompose the motion in two dimensions, that is x direction and y direction. So what you are doing is you are simplifying a two-dimensional problem as a superposition of two one-dimensional problem. Now whatever we have learned in the previous session, we are going to illustrate using two examples in this video. So the first problem is related to acceleration in projectile motion. And this problem says, let us consider the sphere as shown in the figure below. What is her acceleration at each of the point GHI in the figure after she flies off the ramp? Neglect air resistance. So here we have a sphere and there is a ramp. This ramp is used to increase her velocity, and finally she flies off the ramp and she follows a path. Now if I ask what kind of path I will have once she flies off this ramp, so at this point she is here and then she flies off the ramp. Now what kind of path you think it will have? It will have a projectile path, because at this point of time when she is just going to fly, her velocity has two components. Her velocity has x component and also her velocity has a y component, and her velocity is making an angle alpha from the horizontal. So this is the same situation but this we discussed in the previous session, that is equation of motion for projectile. So basically in this case she is going to follow a trajectory and that trajectory will be a projectile. Now we have to neglect the air resistance. So problem says you have to only consider gravity. So acceleration due to gravity you have to consider. You have to neglect the air resistance. What are the things that we have to find? You have to find acceleration at z, h and I. So there are different points that we have. This point is z. So this point is z. So we have to find acceleration at this point, acceleration at this point and acceleration at this point. Now what will be the acceleration? Do we have acceleration in x direction? Since there is no force acting in the x direction, once she leaves the ramp, acceleration in the x direction is 0. What about acceleration in the y direction? Now, once she leaves the ramp, she is flying or she is moving under the gravity. So, at all the point either z, h or I, it's a free fall acceleration. So I can say at each point direction of acceleration in the y direction, the magnitude of acceleration in the y direction is nothing but z. and this is acting in the downward direction. So this acceleration is g, and this is acting in the downward direction. So if I assume my y-axis is upward, then I can say a by E is nothing is equals to minus z, and this is at z h I. So this is very easy. Once he leaves the ramp, the acceleration in the x direction is 0 and the acceleration in the y direction is g. When she is on the ramp, she may have different acceleration in the x direction and y direction because she is changing her speed and also the direction. So she will have both component of acceleration, but once she leaves this ramp, she is completely controlled by the gravity force, and that's why we have only one component of acceleration, that is acceleration in the downward direction, and magnitude will be z and the direction will be in the downward direction. If I consider positive direction as the upward direction, this acceleration will be negative. Now let us discuss the second problem. So this problem is related to a object that is projected horizontally. This means alpha is 0. So from horizontal, the throwing angle, the angle by which it has been thrown is 0 degree. So this means this object is thrown horizontally. So the problem says a motorcycle, a stunt rider rides off the edge of a cliff. Just at the edge, his velocity is horizontal. So this is the motor rider, and when he just leaves the cliff, his velocity is in the horizontal direction with a magnitude of 9 meters per second. So its speed is given, that magnitude in this case is 9 meters per second. Find the motorcycle positions, distance from the edge of the cliff, and the velocity 0.5 seconds after it leaves the edge of the cliff. So we have to find what is the motorcycle position, that is what is x coordinate and what is y coordinate, that is position vector. And then we have to find distance from the edge of the cliff. So distance from the edge of the cliff, so this point. So this is the edge of the cliff. So what we will do is, we will consider this point as origin, that is 0, 0 coordinate. And then we have to find what is the distance, and we have to also find velocity after 0.5 seconds. So let us do one by one. So we have been given time, that is we have to calculate everything after 0.5 seconds. And the initial velocity, magnitude of initial velocity is given. So let's call u is equals to 9 meters per second. So this is given. So initial velocity u is given. Generally I use term u for the initial velocity. So this is given. Now what is my target? My target is to find this coordinate at certain point of time, that is t is equals to 0.5 second. So this will follow a parabola, because once again this is moving under gravity. So a object or a point or a particle moving under gravity follows a projectile path. So this will follow a projectile path, and let's say this is the x coordinate at time t and this is the y coordinate at time t. So we have to find x coordinate and y coordinate. So how will you calculate? Once again, acceleration in the x direction is 0 and acceleration in the y direction is equals to minus g, because my y direction is in the upward direction. Now I can use this formula or expression, s is equals to ut plus half at square, and this formula I can apply in the x direction or I can apply in the y direction. So if I apply in the x direction, I can write x is equals to u velocity in the x direction t plus half into acceleration in the x direction into t square. So this will be, in the x direction speed is 9 meters per second and the time given is 0.5 second, and the acceleration in the x direction is 0. So this term becomes simply 0. So second term is 0. So this is 4.5 meter. So x coordinate now I know, that is 4.5 meter. Now what about y coordinate? So we can apply the same expression in the y direction, that is y is equals to u by t plus half a by t square. Now in the y direction there is no velocity initially, because the total velocity is in the x direction and the magnitude is 9 meter per second. So 0 plus half, and gravity is in the downward direction, so I have to put a negative sign, and t square, t is 0.5 second whole square. Now you can plug the value of z, that is 9.8 meter per second square. So this will be minus half 9.8 meter per second square, and this divided by 0.5 second square. So if you calculate, this value will come minus 1.2 meter. So basically, what is the position? So now I know position, that is x coordinate and y coordinate. X coordinate is 4.5 meter and y coordinate is minus 1.2 meter. So negative sign here shows that the position of motorcycle is below the initial position, and that's why there is a negative sign. So now I can write position vector. Position vector is nothing but x unit vector I plus y unit vector j. So x in this case is 4.5 meter and y is 1.2 meter, and this is j cap and this is I cap. So this is my position vector. So once I know position vector, I can basically calculate the distance. So if you remember, I can source this thing here. So this is my x coordinate, this is my y coordinate, this is initial position of motorcycle, and after certain point of time this is 4.5 meter along the x axis and 1.2 meter along the y axis. So this is the position of motorcycle, that is, this is x distance is 4.5 meter and y distance is 1.2 meter, and if you join origin and final position, that will give you the r vector. You can also calculate magnitude, that is distance from origin to the position, that is nothing but under root x coordinate square plus y coordinate square. Now I know the x distance and y distance, so I can calculate this distance 4.5 whole square plus 1.2, basically this is a negative whole square. So if you calculate this, this will come 4.7 meter. So motorcycle is at a position of 4.7 meter from the origin, and this is in the below side, downward side from the original position. Now we have to also calculate velocity at t is equals to 5.5 seconds. So let us try to calculate velocity at 0.5 second. So once again we have to use the same thing. If you remember, we have formula v is equals to u plus at. Now I will apply this formula for two direction, one for x direction, another for y direction. So if I apply for x direction, I can write Vx is equals to ux plus ax times t. Now a speed in the x direction that was given in the problem, that is nothing but 9 meter per second. What is the acceleration in the x direction? There is no acceleration in the x direction, that is nothing but a speed in the x direction is 9 meter per second. You may remember this fact when we discussed the theory of parabola or projectile motion. We said velocity in x direction remains constant. This does not change with time. Now we can write equation in the y direction. We can write Vy is equals to u by plus acceleration in the y direction times t. And initial velocity in the y direction is 0 and acceleration in the y direction is nothing but minus z, and time in this case is given, that is 0.5 seconds. So this will be minus 9.8 meter per second square times 0.5 second. So this will give you 4.9 meter per second. So now I know x component of velocity and I know y component of velocity. This means now I know velocity vector. Velocity vector is what? X component of velocity times I plus y component of velocity times z, and ij are the unit vector. So now I can write this is nothing but 9 meter per second times I plus 4.9 meter per second times z. Now this 4.9 is with a negative sign, so I have to put this here also. We can show the same thing in a diagram. So this is the initial position of motor bike, and at certain point of time motor bike is here. And this has two components of velocity, one along this direction, that is 9 meter per second. Another along this direction, that is nothing but 4.9 meter per second. And negative sign we already have shown by putting a negative direction of y-axis. Basically in this case my y-axis is in the upward direction, so this is towards the negative side. Resultant velocity will be in this direction. So this is the resultant velocity, and this is the x component of velocity, and this is the y component of velocity. So we can calculate magnitude of velocity, that is speed, is nothing but vx square plus vy square, and then you have to take the under root of that. So this is 9 meter per second whole square plus 4.9 meter per second whole square, and then if you take the root, this value will come 10.2 meter per second. So the object has a speed of 10.2 meter per second after 0.5 second, that is half second. We can also calculate angle. This angle, let's call this angle is alpha or alpha dash or beta, whatever you want to say. For the time being, let's call this angle is alpha. That is the resultant velocity vector. So this angle is what? The angle of resultant velocity vector from the horizontal. So we can write tan alpha. So tan alpha in this case is nothing but Vy divided by Vx. So if you see this triangle, you can basically calculate. So if you see this triangle, what is this? This is Vx, and this is what? Vy, and then this is your resultant velocity, and this angle is alpha. So if I want to write tan alpha is nothing but this divided by this, that is Vy divided by Vx. So this is minus 4.9 divided by 9. So if you calculate this and you take the inverse, or alpha is basically tan inverse or arctan, minus 4.9 divided by 9. So if you calculate this value, you will find alpha is equals to 29 degree. So motorcycle velocity is 29 degree below the horizontal. So you see in this case we calculated the velocity and we calculated the magnitude and direction of velocity. Now see in this problem, the motorbike has only horizontal speed. This does not have any vertical speed. So this means in the vertical direction, the motion is same as free fall acceleration. So you can directly calculate by or v in vertical direction if you use the concept of one-dimensional motion and free fall in the vertical direction. For example, if you want to calculate what is the y coordinate after half second, you can simply use one dimensional free fall expression, that is nothing but minus half gt square, and this is minus half into 9.8 meter per second square, and this is in this case 0.5 second square. So you can calculate y value, which is equals to minus 1.2 meter. So the idea is, in the vertical direction, the motion is very simple. This is one dimensional free fall, because the velocity imparted to the motorcycle is only in the x direction. This does not have a bidirectional velocity. So I can simply treat motion in the vertical direction is one dimensional free fall acceleration. So I hope you enjoyed this video, and if you like this video, please share with your friends, and I will see you in the next video. For the time being, thank you, and I will see you in the next video. Bye. Hello friends. In the last few videos, we discussed about the projectile motion, and we said the key idea of solving problems related to projectile motion is the superposition. Basically, when you have a projectile motion, this is a two-dimensional motion. So what we do is we decompose this problem into one-dimensional problems. So we separate x-axis motion and y-axis motion, and we analyze these two directions motion, and we write equation and we solve the problems. Now in this video we'll see how to calculate maximum height, time of flight, and range of a projectile when this projectile is thrown on a horizontal plane. So let us consider this is my y-axis and this is my x-axis, and a projectile is thrown with initial speed u at angle alpha. So this is the path of the projectile that it will follow. So this is the projectile path. So at certain point of time it will reach maximum height. So let's say this maximum height is somewhere here. So we have to find what is this maximum height. So maximum height is the height reached by the projectile, which is maximum for the duration when it is in the air. Another term we have, that is time of flight. So what is the time for which this projectile remains in the air? So we'll call this maximum height as h, time of flight with t, and the range, that is the distance covered on horizontal plane, that is called range. That is from launching point to the landing point. So on the horizontal plane, what is the distance between launching and landing point? That we will call as range. So in this video we will try to find these three terms and how we can calculate expression for these three things. Once again, to solve this kind of problem, we have to first write what is the velocity in the x direction, what is the velocity in the y direction. So if you decompose this velocity vector, in the x direction you can write velocity is equals to u cos alpha, and in the y direction this velocity has a component of u sin alpha. Now there is no acceleration in the x direction, so we can say x is equals to 0, and there is acceleration in the y direction, that is acceleration due to gravity, and this is in the downward direction, and I have chosen y direction is the upward direction, so this will be minus g. So now I have this, I want to calculate these things, that is height, time of flight, and range of projectile. So let us first focus on calculating height. So we want to calculate what is the maximum height that this projectile will reach. How we will find the maximum height? What is the key idea? The key idea is when this reaches to the maximum height, that is this point, this will have y direction velocity is 0, because if there is a still y velocity, In that case, it will go still further. So this means this will not be the maximum height. So this means when you have maximum height, there is no velocity in the y direction. This is the key point, that is v by is equals to 0. Mathematically, this is same as dy by dt is equals to 0. So y is maximum, and y is maximum, this is nothing but maximum height it reached by this projectile. So we'll use this fact that Vy is equals to 0 to calculate the maximum height reached by this projectile. So let us write velocity Vy as a function of time. So we can write, now I can use this expression v is equals to u plus at. If you remember, I can use this expression kinematical equation. Now I can use this in the y direction. So I will write Vy is equals to u by plus a by times t. So what is initial velocity in the y direction? In this case, initial velocity in the y direction is u sine alpha. So this is initial velocity plus acceleration. Acceleration in the y direction is minus g and times t. Now as I said, when I will have maximum height, v by is equals to 0. So this term is equals to 0. So from here I can calculate time, and this is the time, that is u sine alpha divided by z. This is the time then maximum height will be reached. So after this point of time, maximum height will be reached. Now once I know the time, I can use formula s is equals to ut plus half at square to calculate the maximum height. So let us use the formula, that is s is equals to ut plus half at square to calculate the maximum height. Now once again, I will write this equation in the y direction. So I will write y is equals to u by t plus half a by t square. So let us calculate this y. Y is equals to, what is the initial velocity in the y direction? That is nothing but u sine alpha. What is the time when I want to calculate y, that is maximum height reached? And this we just calculated. This is u sine alpha divided by z plus half. What is the acceleration? Acceleration is minus z, because this is acting in the downward direction. What is time? This is the same time that we just calculated, u sine alpha by z, and this is raised to the power 2. So from here I can calculate y. Y is nothing but u square sine square alpha divided by z minus half, and this will become u square sine square alpha divided by z. You see, this term and this term is same. Only thing is there is a difference of 1 by 2, coefficient of 1 by 2. So if you subtract this from this, you will get u square sine square alpha divided by 2z. So this is the maximum height reached by the projectile. So I can say maximum height is nothing but u square sine square alpha divided by 2z. You can write same thing, u sine alpha divide whole square, and this divided by 2z. So u sine alpha is nothing but vertical velocity, initial vertical velocity. So one can also remember this is nothing but u by a square divided by 2z. So this is the maximum height reached by the projectile. Now let us come to time of flight, that is the time for which this projectile is in the air. So we want to calculate time of flight. So what will be the key point when we are calculating time of flight? Can you tell me what will be the key point? This is the projectile and this is the path. So when we want to calculate time of flight, we can use the key idea, that is at one point of time, that is t is equals to 0, this is at origin, that is y coordinate is 0. At again t is equals to t, the y coordinate is again 0. This means there are 2 points of time when y is equals to 0. So what we will do is, we will write expression for y, the displacement in the y direction. And once I write that expression, I can equate that is equals to 0, from where I can get the time. So what is the idea? I will plug y is equals to 0, and from there I will get time. So let us try to do this. So how will you calculate y? If you remember, s is equals to ut plus half at square formula, and I will apply this formula in the y direction. So I will write y is equals to u by t plus half acceleration in the y direction t square. So y is equals to, what is the initial velocity in the y direction? This is nothing but u sine alpha t plus half, what is the acceleration in the y direction? Minus g t square. And now we have to equate this is equals to 0. So I have to equate this with 0. So let's take t common. So I can write the same expression, that is u sine alpha minus gt divided by 2. This is equals to 0. So this gives two value of t. T is equals to 0, and so this is one expression. Another is t is equals to 2u sine alpha divided by z. So there are two root of t, and this is obvious because this expression is quadratic in t. What this means? Y value is 0 at t is equals to 0, and the y value is also 0 at this t, that is 2u sine alpha by z. And this time is nothing but time of flight, that is the total time for which this projectile is in the air. So this time is nothing but time of flight, so we can write time of flight is equals to 2u sine alpha divided by z. Now finally we can also calculate range. So how will you calculate range? So what is the idea? What is the key idea for calculation of range? Once again, the key idea is, we can use the fact that there is a velocity in the x direction, and this projectile has been in the air for time capital T. So if I take x direction equation, I will get range. So let us apply this expression, s is equals to ut plus half at square, and apply this in the x direction. So x direction ux into t, and acceleration is 0. So what is x? X direction initial velocity is equals to u cos alpha. And what time I am interested? I am interested in total time. Then I will get range, the total time for which this projectile was in the air. So u cos alpha times total time, that is time of flight. Now I know expression for time of flight. I can plug this value, that is 2u sine alpha divided by z. From here I can write u square sine alpha cos alpha, and this divided by z multiplied by 2 also. There is a formula in algebra, that is 2 sine alpha cos alpha can also be written as sine 2 alpha. So this is u square sine 2 alpha, and this divided by z. So this is the expression for range. So now we calculated range. So range is equals to u square sine 2 alpha divided by z. So this is the horizontal distance that the projectile will cover in time of flight, that is the total time that was in the air. So we calculated the horizontal range, time of flight, and the maximum vertical height, that is maximum height reached by the projectile. Now we will try to see some special cases for height and range. So what was the expression for maximum height? The maximum height is u square sine square alpha divided by 2z. So this was the expression that we derived. Now if u is fixed, when the maximum height will be reached? So this means I have fixed u, but I am changing alpha. So alpha is changing. What this means? This means I have a velocity that is fixed. But now angle is not fixed. I can throw at this angle, or I can throw at this angle, or I can throw at this angle. So projectile angle by which I am throwing is not fixed, but u is fixed. Then I am asking for what alpha, for what angle this h will be maximum. So h will be maximum only when sine square alpha is maximum. So what this means, I can say h is maximum when sine square alpha is maximum. And when sine square alpha is maximum, you know maximum value of sine alpha is 1, and this can happen only if alpha is equals to 90 degree. This means if you want to a maximum height, you have to throw vertically up. So you have to throw vertically up. So if you have u is given and you want to maximum height attained by the projectile, you have to simply throw in the vertical direction. Now what will happen if alpha is equals to 0 degree? In that case, h is equals to 0 because sine alpha is equals to 0. In that case, no maximum height will be reached. Basically, in that case, what you are doing is you are throwing projectile horizontally. So no maximum height will be reached in that case. Now next question is when range will be maximum. So we have expression for range. Range is nothing but u square sine 2 alpha and this divided by z. Now when this range will be maximum? So if I want my range to be maximum, this means what? This means u is given, u is fixed. So u is fixed. I can only change the angle. This is possible only if sine 2 alpha is maximum. So if I have sine 2 alpha that is maximum, then I will have maximum range. So for maximum range, I can say sine 2 alpha is equals to 1. This is possible because maximum value of sine alpha or sine theta is equals to 1. And this is possible when 2 alpha is equals to 90 degree. This also means alpha is equals to 45 degree. So if you throw an projectile at angle of 45 degree, you will have maximum range. So if you want to maximize the range, so let's say this is the projectile, and if you want to maximize the range, in that case you have to throw this projectile at angle of 45 degree. If you throw any lesser angle, it will not reach, it will not go up to this distance. It will basically fall somewhere here, somewhere here. So if you want to maximize for a given velocity, you have to throw at angle of 45 degree. Another important point about the range. So what is the expression for range? Range is u square sine 2 alpha divided by z. Now in this expression, if I plug 90 minus alpha in place of alpha, what will be the range? Range is equals to u square sine 2 times 90 minus alpha divided by z. So this is nothing but u square sine 180 degree minus 2 alpha divided by z. And if you have some idea of algebra, you can say sine of 180 minus theta is equals to sine theta. So from here I can say this is again same as u square sine 2 alpha divided by z. So this gives me one important result, that is if I throw a projectile either at angle alpha or at angle 90 minus alpha, both will give the same range. For example, if I take alpha is equals to 30 degree, then what will the value of 90 minus alpha? 90 minus alpha will be 60 degree. This means if I throw a projectile either at angle of 30 degree or at angle of 60 degree, in both case range will be same. And this I can show in this diagram. So let's say if I am throwing a projectile at a angle of 30 degree, in this case this is the range. Now the same, if I throw at angle of 60 degree, so this is 60 degree, so this is 30 degree, this is 60 degree. In this case again, this projectile will also have the same range, that is range value for both cases are same. So this is the range in both cases. Mind, in both cases this is not maximum, this is less than maximum. So this is maximum range and this, let's call this as range. So this range is less than maximum range, but both are equal. So if you are throwing a ball at angle of 30 degree or 60 degree, in other words you can say this is same amount of angle from the 45 degree downside, another is upside. So what is the difference between 45 degree and 30 degree? Difference is 15 degree. What is the difference between 60 degree and 45 degree? Again 15 degree. This means if you are throwing a ball, so this is 45 degree angle. So either you throw 15 degree this side or you throw 15 degree that side. In both cases you will have same range. This is not only true for 15 degree, this is true for any angle theta. So from any angle theta, this side from the 45 degree line and any angle theta, this side from the 45 degree line will have same range. This is very important result if you are throwing a ball at the angle of alpha or you are throwing at angle of 90 minus alpha. In both cases you will have the same range. So we derived expression for range, maximum height and time of flight. Remember, you don't have to memorize these formulas. The reason is, in deriving these formulas we have made some assumption. The first assumption is the launching point and the landing point both lies on a horizontal plane. You will see in next lecture that if you have an inclined plane, how do you calculate the time of flight, range and maximum height. So I hope you have enjoyed this video, and if you enjoyed this video, please share with your friends, and I will see you in the next video. Thank you. Bye. Take care. Hello friends. In the last video we have seen how to calculate time of flight, how to calculate range and the maximum height in case of a projectile motion. And we have also seen how we can solve the problem related to projectile motion. In that case, we have to write equation of motion along the x direction and along the y direction. And then once you have these equations, that is kinematical equation, you can solve for the unknown. Now let's try to use all this to solve a problem. And this problem is related to ball hitting the ground. So this problem says you throw a ball from your window which is 8 meters above the ground. So this is your window and this window is 8 meters off the ground. So ground is somewhere here. And the height of window from the ground is given, that is 8 meters. So this height is 8 meters. That is given. Now the question further says, when the ball leaves your hand, it is moving at a speed of 10 meters per second at an angle of 20 degrees below the horizontal. So when this ball leaves your hand, this is moving at a speed of 10 meters per second. So initial velocity is given, that is 10 meters per second. And angle on which this has been thrown, that is also given. So this is 20 degree angle and this is below the horizontal. So this is your horizontal line. And since the velocity is below the horizontal, that's why this angle is negative. So negative 20 degree angle. The question asks, how far horizontally from your window will the ball hit the ground? Ignore air resistance. Now once this ball leaves your hand, it will follow a projectile and the path will be parabolic. As we discussed in the previous classes, in this case the path will be parabola. So somewhere, let's say this hits the ground at this point. So we have to find what is this distance. So we have to calculate this distance. Now we know this distance. The vertical distance is known to me and the horizontal distance we have to find. So how will you solve the problem? First, let us see what are the things that is given. You have been given initial velocity, that is 10 meter per second. Angle alpha is also given, that is negative 20 degree. And the y value, this is also given, that is minus 8 meter. So what this means, let's say for doing this problem, set a coordinate axis. So this is my x-axis and this is my y-axis. So when ball hits the ground, this is the point. So what is the coordinate of this point? X coordinate we have to find. I don't know the x coordinate, but I know the y coordinate because this distance is known to me and this distance is nothing but 8 meter. But this is negative side of the y-axis. My y-axis is upside. So this coordinate, that is negative side of the y-axis, is minus 8. So I can say y is nothing but minus 8 meter. And the question says you have to find what is the value of x. What is the distance this ball is from the window in horizontal direction. So horizontal direction is x meter. So we have to find x. So how will you solve this problem? Remember, whenever we are trying to solve such problem, we have to write kinematical equation in x direction and the y direction. So what is the things that is given? So we have been given y and we have been given initial velocity u. So these two things are given. So now I can use kinematics to find time because I know s is equals to ut plus half at t square. Once I know time, I can calculate x because I know the velocity in the x direction and I can multiply with the time and I will get x. So let us try to use all this to solve this problem. So if you remember, we have for distance the kinematical equation is s is equals to ut plus half at square. I can also write, if I am writing this equation in the y direction, I have to write y component of distance. This is y component of velocity, that is u by t plus half, and acceleration in the y direction is minus g. Minus g, why? Because I have taken positive direction upward side. So gravity is basically acting in the downward direction. So I have to account for the sign. So this is minus g. Now let us try to write this equation. So I know basically y. So first I will find an expression. So y is equals to u by, what is u by? So this is u. I can take component. So in this direction I will have u cos alpha and in this direction I will have u sin alpha. So u by is nothing but u sin alpha. Alpha is known, u is known. So I can write u sin alpha times t minus, this will become half gt square. So from here I can calculate t. Now I can rearrange this expression and I can write half gt square minus u sin alpha into t plus y is equals to 0. This equation is quadratic in t. So I have to solve for t. So we can solve for t. And if you have a quadratic equation, you know root is given by minus b plus minus b square minus 4ac divided by 2a. So I am assuming that you know how to solve a quadratic equation. And the root can be given as, so in this case time, there will be two root t1 and t2 and this root can be given as minus b. So in this case b is minus u sine alpha. So this becomes u sine alpha. Minus b plus minus a square root of b a square. So minus u sine alpha whole square. Minus 4ac. So 4a is nothing but half z. 4ac. And what is c? C is nothing but by. 4ac divided by twice a. And a is nothing but half z. So from here we can calculate t1, t2. So this will be u sine alpha plus minus a square root u square sine square alpha, and this becomes minus 2z by, and this divided by simply z. Now I can plug the numerical value and I can calculate two different time. So u is given, that is nothing but 10 meter per second, and sine alpha is nothing but minus 20 degree, and this is plus minus a square root of u is given, that is 10 meter per second, and sine 20 degree. So this is sine 20 degree with a negative sign. So this is sine of minus 20 degree, and this is a square, and 10 meter per second, this is also a square. Minus 2 into 9.8 meter per second, this is z per second square, and then by is nothing but negative 8 meter, and this divided by z, that is 9.8 meter per second square. Now if you solve, you will find two time. One is minus 1.7 second, another is 0.98 second. So one root is negative, another root is positive. Negative root has no meaning because this basically tells about before the ball has thrown. So 0 time starts from ball has been thrown. So this negative is before the throwing the ball. So this has no physical meaning. So this time has no physical meaning. So time in this case only 0.98 second. So this means ball is going to hit the ground after 0.98 second. So once I know that after this much amount of time this ball is going to hit the ground, I can calculate how much distance this ball will cover to the ground. This means I can calculate this distance because I know the time. So what I have to do? I have to write equation of motion along the x direction. So this is my x direction. I can again use s is equals to ut plus half at square formula, and we can calculate x. So x will be velocity in the x direction is u cos alpha, and time I know that is 0.98 second, and acceleration in the x direction is 0. So u is 10 meter per second, and cos of minus 20 degree, and time is 0.98 second. So if you calculate this, this will come 9.2 meter. This means ball is going to hit the ground at a distance of 9.8 meter, and the vertical distance is nothing but 8 meter. So we can basically write position vector of this point. So what is the coordinate where the ball is going to hit? So x coordinate is minus, basically x coordinate is 9.8 meter, 9.8 meter, and the y coordinate is minus 8 meter. So now I can write this position vector. So what is the position vector of the point where this hits to the ground? So position vector is nothing but xi plus by j, xi plus by j. So in this case x is nothing but 9.8 meter, and this I cap plus minus 8 meter, and this is nothing but j cap. Basically we can also find this distance, the distance from origin where it hits the ground. In that case I have to take the magnitude of the position vector, that is under root x square plus by square. This is 9.8 meter whole square plus 8 meter whole square, which is equals to 12.64 meter. So in this video we have seen how we can calculate horizontal distance when you are throwing a ball from your window, or you can have similar situation at some other places also. Then you can calculate the horizontal distance. What is the idea? First idea is you have to think in terms of two equations. First I wrote bidirection kinematics, and then I wrote x direction kinematics. From there I got the x, that is the coordinate from the horizon, from the vertical line crossing through the window to the point where this is a ball is crossing to the ground, ball is falling to the ground. So I hope you enjoyed this video, and if you enjoy, please share with your friends, and I will see you in the next video. For the time being, see you, bye, take care. Hello friends, in this video we will do a problem on projectile motion, and this is an interesting problem. In this problem we will see we have two projectiles, and these two projectiles are going to collide. So there are many problems of this type. To solve such problems, what we have to do is we have to find the x coordinate of projectile 1 and x coordinate of projectile 2, similarly by coordinate of both projectiles, and we try to make some kind of constraint, some kind of equality in these terms, and then we solve the problems. So let us try to learn to solve projectile motion problems that involves two projectiles. So this problem says, so this is basically, this problem is also called zookeeper and monkey problem. So problem says a monkey escapes from the zoo and climbs a tree. So now monkey is on a tree. After failing to entice the monkey down, the zookeeper fires a tranquilizer dart directly at the monkey as shown in the figure. So this is the monkey here, and this monkey is hanging from a tree. And here we have zookeeper. So this zookeeper is not able to catch the monkey or not able to entice the monkey to come down. So now he is using different methods. So what he is doing is he is throwing a tranquilizer dart, and he is throwing in this direction. So this is the direction of tranquilizer dart. The monkey lets go at the instant the dart leaves the gun. So as soon as monkey sees that he has thrown a dart, and at the same point of time he leaves and he tries to go down with as a free fall. So we have to show that the dart will always hit the monkey, provided that the dart reaches the monkey before he hits the ground. So we have to show that the dart is going to hit the monkey. So how will you solve this problem? So first let us see what are the things that is given. So we have been given initial velocity of dart. Let's say this dart is thrown at a speed of u and angle alpha from the horizontal. So this is given. Let's say this tree is at a distance d from the zookeeper. So this distance is also given. And to solve this problem, we will need to have a coordinate system. So let's say we define a coordinate system. This is my x-axis and this is my y-axis. So y-axis is vertically up. This means my gravitation that is acting in the downward direction will be negative. Now this is the dart. So initially basically dart is aiming to the monkey. So we can calculate this distance. So this distance can be calculated. So we can calculate this distance because in this triangle, you see this triangle and this triangle, alpha is known and d is known. So we can calculate this distance. So if I write tan alpha, let's call this distance is x. So we will have x by d. This means x is equals to d tan alpha. So basically I know this distance. This is nothing but d tan alpha. So what is the initial height of monkey from the ground? That height is simply d tan alpha. Now you see, this problem basically has two projectiles. One projectile, the monkey. Monkey is falling freely in the downward direction. Of course, this is a very simple projectile that moves in a straight line, vertical line. That is also a special case of projectile. The dot will follow a projectile and it will have a parabolic path. So this is the path of dart. So dart is basically following a projectile path, and this monkey is following a simply free fall path, a straight line path. So this is the path of monkey and this is the path of dart. So there are two projectiles, and we have to find the condition so that this dart is going to basically collide with the monkey. So at the point where it will have collision, I can say, let's say it has a coordinate of x and y. So what we can do is, we can find x coordinate of dart and we can find x coordinate of monkey. Similarly, I can find y coordinate of dart and y coordinate of monkey. If there is a collision or if there is a hitting, then these two coordinates should be equal. What all this means? This means I can calculate x coordinate of dart at any given point of time. Let's say I know my time. So for a given time, I can calculate x coordinate of dart, and I can also calculate x coordinate of, in this case, monkey. And since there is a hitting, these two x coordinates should be equal. Similarly, if x coordinate is equal, then their y coordinate also should be equal. So for hitting, y coordinate of dart should be equals to y coordinate of monkey. So what I will do is, I will first consider x coordinates are equal, and from there I will calculate time. So from this I will calculate time, and once I know the time, I will basically put this time and check whether y coordinates are equal or not. If this is equal, this means the dart is going to hit the monkey. So let us try to find x coordinate of dart, and we will use same formula, s is equals to ut plus half at square. Now as you remember, in x direction there is no acceleration, so ax is equals to 0, and ay, there is acceleration in the downward direction, that is simply minus g. This is true either for dart or this is also true for monkey. Now I am writing for dart. What is the initial speed of dart in the x direction and in the y direction? So basically I can write initial speed of dart in the x direction. What is this speed? So in this direction we have a speed of u, and this angle is alpha. So in this direction we have a speed of u cos alpha. Similarly, what is the speed of dart in the y direction? In this direction we will have a speed of u sin alpha. So now I know a speed in x direction and y direction. So now I can calculate x dart is equals to a speed in the x direction of the dart, that is simply u cos alpha, and this times time, plus acceleration in the x direction is 0. Now from figure you can also calculate what is x dart, since collision happens at this point and I know this distance is nothing but equal to d. So the monkey is at a distance d from the origin in the horizontal direction. So I can plug x dot is equals to d, and this is equals to u cos alpha times d. So from here I can calculate time, and this turns out to be d divided by u cos alpha. So this is the time after which the dot is going to hit the monkey. So we have done the first part, that is, we have equated the x coordinate and we calculated the time. Now we can go to the next part. Using this time, calculate the y coordinate of monkey and y coordinate of dot, and if these two are equal, I will say this is going to hit, dot is going to hit the monkey. So what is the next step? So next step is to calculate y coordinate of dot, or what is the y distance of the dot. In figure I can show the same thing. So this distance is the y distance. So we can calculate this distance. Again I will use the same formula, ut plus half at square. In this case, velocity in the y direction, initial velocity in the y direction, that is nothing but u sine alpha. So this is u sine alpha times t plus half gt square. Now acceleration in the y direction is negative because my y-axis is in the upward direction, and this multiplied by t square. So now I know y dot is equals to u sine alpha, and time I know, time is nothing but d divided by u cos alpha plus half minus z, and time I can again put here, that is d by u cos alpha. So if you simplify this, this will be simply d tan alpha, and this is negative gd square divided by 2u square cos square alpha. So this is the y coordinate of dot. Since I know the time because I have equated the x coordinate. Now I will calculate y coordinate of monkey. So how will you calculate the y coordinate of monkey? So basically, monkey is freely falling from this point, and this has fallen to time t by this distance. So we can calculate this distance. This distance is nothing but half gt square because initial velocity of monkey is 0 in the y direction. So this distance is nothing but half gt square. I am talking about the distance without the sign. This distance is without the sign is half gt square. So what is the y coordinate of monkey? This coordinate is nothing but total minus this distance. So total is d tan alpha. So total distance is d tan alpha minus this distance, that is half gt square. That will give you y coordinate of dot. So y coordinate of monkey is nothing but d tan alpha. And from where I am getting d tan alpha? Because initially I said in this triangle I know d. So I know this vertical height, that is d tan alpha, and this distance is nothing but half gt square. So d tan alpha minus half gt square is nothing but y coordinate of monkey, and this is d tan alpha minus half z, and t I know, that is nothing but d divided by u cos alpha. So now you see d tan alpha minus half z d square divided by u square cos square alpha. So this is y coordinate of monkey when they are going to hit. Now you see this term, that is y coordinate of monkey and y coordinate of dot. So this term and this term is same. The first term is d tan alpha, first term is d tan alpha, and the second term is simply half gt square, that is gd square by 2u square cos square alpha. So second term is also equal. This means by dot is equals to by monkey. This means dart is going to hit the monkey, and this is true for any time. So this means it has to hit dart has to hit the monkey, because in both cases this is a basically free fall acceleration, and that's why monkey will be always hit by the dart. Moreover, there is two important points. One is you can have any value of u. This by coordinate of dart and by coordinate of monkey will be same, because this is independent of u. So whatever the value you put here, you will get the same expression of y dart and same expression for monkey. So it does not depend upon with what velocity you are throwing the dart. So it is independent from initial speed of the dart. Similarly, this also does not depend upon value of z. That is, either you can take gravity value 9.8 or you can take 10. So whatever the value of z you have, this will basically effect, or this will be reflected in both equation, y dart as well as y monkey. So finally the y dart and y monkey will be same. So this formulation is independent from initial speed of the dart, and this is also independent from the gravity, the value of gravity. You can either do this exercise at some places where you have gravity lesser, some places where you have gravity higher. Both cases the dart is going to hit the monkey. In fact, there is a special case when g is equals to 0. What will happen if g is equals to 0? In that case, your monkey is not going to fall. So this is the position of monkey. So this is monkey position. So if z is equals to 0, monkey is not going to fall, and this dart will basically cover this path, that is a straight line path. This is also not going to be deflected because there is no gravity. So gravity is absent. So this will go basically in a straight line path, and this will hit to the monkey. So if there is no gravity, the dart will follow a straight line path, monkey will remain at the same position, and this dart is going to hit the monkey. So in this video we learned how to basically solve a problem related to collision of two projectiles. In that case, what you have to do is, you have to basically first equate one of the coordinate and then find time or any other variable, and then using that variable try to see whether other coordinates are equal or not, in this case by coordinate. I hope you enjoyed this video, and if you enjoy, please share with your friends so that more video can be made for you, and I will see you in the next video. For the time being, thank you and see you in the next video. Bye.